Eu percebi aqui que os outros palestrantes ainda não conectaram, né?
Os da próxima sessão.
Ainda falta a Amitava, o Babatunde.
O Babatunde está aqui, vou promover ele. Acho que talvez algum esteja entrando com um link de participante, porque o e-mail de convidado para alguns está indo para a caixa de spam.
Tá.
Okay. Good afternoon, Professor.
So, hi. Let me see.
Okay.
Hi.
Hi.
Hello, Professor.
Good afternoon.
Yeah, afternoon. Thank you.
Good afternoon.
Draw cutting away. To be
Ok, João. Podemos começar. Acho que eu faço uma pequena introdução da sessão de hoje. Aí depois Fábio assume como chair dessa manhã.
Ok, já está gravando.
Okay. Good morning, everybody. Thank you so much for coming. We are pleasure to start our third day of the International Symposium Physics. Today, our session is going to be about upper atmosphere and the ionosphere. And we are pleasure to receive important names in the astronomy field around the world. Thank you so much for the speaker that kindly accept to participate of this meeting. And during this morning session, we're going to have the talk of Professor Miyoshi, Professor Amitava Guharay, Professor Babatunde Rabiu, Dr. Sivakandan, and Professor Manilo Marques. Dr. Fabio, please go ahead and introduce this morning section.
Thank you, Igor. Good morning, everyone. Good afternoon. Good evening. Let's start this session. Our first speaker is Dr. Yasunobu Miyoshi, who is associate professor at the Department of Earth and Planetary Sciences in Kyushu University in Japan. Dr. Miyoshi is an expert in middle atmospheric science, and he is also an expert in atmospheric modeling. Dr. Miyoshi, it's a pleasure to have you here. Your talk is about 45 minutes, and we think we can have 35 minutes and more 10 minutes for questions and discussions.
Thank you. Can I share my PowerPoint file?
Yes, you can, Professor. And there's a share button. Okay.
Thank you, João.
Okay. Okay. Can you hear?
Yes, we are listening, but we please ask you to put in the full screen if you could, or in the presentation mode.
Okay. Okay. Okay.
No, we are not.
Please share it now.
Okay, no?
Not yet.
Okay.
No, we are not seeing the slide.
Yet.
Not? Oh.
I guess you have to share your screen again. Yes.
No.
Okay.
Okay.
And now put in.
Yes, we are seeing your screen now. Mom, you can't see your screen.
Okay, no?
Not yet.
It was before.
It was before. Oh. Oh, sounds of some trouble. Okay. Okay, no?
Not yet.
No, not yet.
Yes, it's starting.
Okay.
Yeah, we can see the.
Yeah, okay, yes.
Okay.
Yes, thank you, Chairman. I would like to talk about variability of the ionosphere thermosphere system. Outline of my talk is as follows. At first, I introduce Kyushu University. As you know, Japan is located on the opposite side of the Earth from Brazil, so local time difference is 12 hours. And Kyushu University is located in Fukuoka City, and Fukuoka City is west part of Japan, is located here. And Kyushu University was founded in 1903, more than 100 years ago. And the number of undergraduate students in Kyushu University is about 15,000, and the number of graduate students is about 6,500. If you are interested in Kyushu University, please come to Fukuoka, Japan, okay? Next, we show the thermosphere variation. This figure shows longitude, latitude distribution of temperature and wind under solar minimum and solar maximum condition. This is simulation result. Temperature and the magnitude of wind is sensitive to solar activity. The temperature at solar maximum is about 500 to 700 Kelvin higher than the temperature at solar minimum. And diurnal variation is also dominant in the thermosphere. Can you see the movie? No?
No, we can't.
No.
Yes.
Can you see movie?
Yes, now we can see the movie.
Yes. This movie shows the diurnal variation of temperature and wind at 400 kilometer height. One step is 1 hour. You can see the high temperature in daytime and low temperature in nighttime. This circulation pattern moves westward with a period of 1 day. So this 1 day's pattern is generated by absorption of solar radiation. So this means that diurnal variation due to solar radiation is dominant in the thermosphere. On the other hand, this movie shows the circulation pattern in the upper troposphere. This is a temperature and wind pattern at 8-kilometer height. One step is 6 hours. High temperature is located at low latitude, and wave pattern is very dominant. Wave pattern is important in middle and high latitude. This wave pattern is due to baroclinic wave, namely eastward moving high and low pressure system. And very strong eastward jet is located at middle latitude. This means the circulation pattern in troposphere is quite different from the circulation pattern in thermosphere. These figures show the temperature and wind pattern at various heights. Upper left figure is circulation pattern in the upper troposphere, and upper middle figure shows the circulation pattern in the stratosphere, and upper right figure shows the circulation pattern in mesosphere, and lower left figure is circulation pattern in the lower stratosphere, and lower middle panel shows circulation pattern in thermosphere. In troposphere, baroclinic wave is dominant, and in the stratosphere, large-scale planetary wave pattern is dominant. And in the mesosphere and the lower thermosphere, small-scale gravity wave is dominant. And in upper thermosphere, large-scale diurnal variation is dominant. This means the circulation pattern in the thermosphere is quite different from the circulation pattern in the lower atmosphere or middle atmosphere. This is very important features. Next, we show the electron density in the ionosphere. Left figure is the temperature and wind pattern in thermosphere about at 400 kilometer height, and right figure is electron density at 300 kilometer height. Diurnal variation is very dominant in thermosphere and ionosphere, but in the ionosphere, electron density has a peak around 15 degrees geomagnetic latitude. On the other hand, temperature maximum in the thermosphere is located near the equator. It is some difference between thermosphere and ionosphere. This panel shows the variability of the ionosphere-thermosphere system. This figure is from Forbes paper. Energy input from above, such as particle precipitations from magnetosphere and solar UV and EUV radiation are important in the ionosphere-thermosphere system. So this means that energy input from above plays an important role in the ionosphere-thermosphere system. However, recent studies have revealed atmospheric waves that propagate vertically from the lower atmosphere affect variability of the ionosphere-thermosphere system. In this talk, we introduce impact of atmospheric waves from below on the ionosphere-thermosphere system. Green color indicate energy input from above, and blue color indicate atmospheric waves from the lower atmosphere. In the upper atmosphere, satellite and ground-based observation are very important to investigate variability of the ionosphere-thermosphere system. But temperature and wind distributions in the whole atmospheric regions are necessary to investigate vertical propagation of atmospheric waves from the troposphere to the thermosphere. This means that in order to investigate vertical coupling process between lower and upper atmosphere, temperature distribution and wind distribution in the whole atmospheric region are necessary. However, horizontal and vertical coverages and temperature resolution of satellite or ground-based observation have limitations. So a whole atmosphere ionosphere model that contains the region from the ground surface to the upper thermosphere ionosphere is a very useful tool to study vertical propagation of atmospheric waves from the lower atmosphere to the upper atmosphere. Our group have developed an atmosphere ionosphere model GAIA. In this talk, we introduce GAIA and some example of vertical propagating waves. This panel describes our atmosphere ionosphere coupled model GAIA. GAIA is a ground to topside model of atmosphere and ionosphere for aeronomy. So this model contains a region from ground surface to upper thermosphere and ionosphere. So this model can simulate coupling process between neutrals and plasmas. Also, this model can simulate coupling process between the lower atmosphere and upper atmosphere. GAIA have been developed by coupling 3 different models: neutral atmosphere model and ionosphere model and electrodynamics model. The details of this model are described in Jing et al. 2011 paper. If you are interested in the GAIA model, please check this paper. This panel describes GCM of neutral part of GAIA. The GCM, general circulation model of neutral atmosphere, solves the full nonlinear equations, such as eastward momentum equation, northward momentum equation, thermodynamics equation, hydrodynamics equation, and continuity equation at each grid point. Grid point in the model are shown in lower right figure. The GCM includes physical processes such as effect of boundary layer process, solar and infrared radiation, moist convection, hydrology, and molecular and eddy diffusions, ion drag force, Joule heating, and so on. So these physical processes are also very important to simulate realistic circulation in the atmosphere. Details are described in Miyoshi and Fujiwara 2003 GRL paper. These nonlinear equations are solved at each grid point. The number of grid points in the model is about 1 million for low resolution model, and the number of grid points is about 30 million for high resolution model. So there are many grid points. So we have to solve these nonlinear equations at each grid point. So huge computational time and memory are necessary to conduct GAIA simulation. So supercomputer system is necessary to simulate GAIA model. Left figure shows a supercomputer system ITO at Kyushu University. We use this supercomputer system to conduct GAIA simulation. This panel describes the method to solve momentum equation. Momentum equation includes nonlinear term colored by blue, the Coriolis term colored by red, colored by green, and pressure gradient force colored by orange, and physical processes. These terms are estimated at every time step. And by integrating this momentum equation like this, and zonal wind predicted by using this formula. Physical processes such as friction at ground surface, eddy diffusion, ion drag force, molecular diffusion, gravity wave parameterization are very important to simulate realistic circulation in the whole atmosphere. In particular, in the thermosphere, ion drag force, molecular diffusion, gravity wave drag parameterization are very important. We estimate this acceleration rate at each grid time step and calculate and predict zonal wind. This panel describes the method to solve thermodynamic equation. The method to solve thermodynamic equation is similar to the method for momentum equation. In thermodynamic equation, diabatic forcing term is very important. In the troposphere, diabatic heating by moist convection, solar and infrared radiation, and sensible heat exchange between ground surface and atmosphere are very important. And in the thermosphere, diabatic heating by thermal conductivity, Joule heating, and auroral precipitation heating are important to simulate the thermospheric circulation. We estimate this diabatic heating rate at each time step and predict temperature evolution. This panel shows the ionosphere and electrodynamic model. The ionosphere model solves the full nonlinear equation of mass, momentum, and energy for major ion species and electrons. The ionosphere model also incorporates production and loss due to photochemical reactions, as well as ion diffusion and convection processes. The details of ion model is explained in Shiragawa-san's paper. In electrodynamics model treats the closure of global ionospheric currents induced both by neutral wind dynamo and by setup of polarization electric field. The electrodynamic model assumes geomagnetic lines are equipotential and solve electrodynamic processes in this model. Next, we show southern stratosphere warming event and its impact on the ionosphere thermosphere system. Southern stratosphere warming is an event that polar stratospheric temperature rises by several tens of kelvins within a week. Left figure shows time, height distribution of temperature at North Pole. you can see the temperature rises abruptly on mid-January. Temperature rise by about 60 or 70 Kelvin within a week. Right figure is the time height distribution of zonal wind at 60° north latitude. Positive value is eastward wind, and negative value is westward wind. Eastward wind is very strong in December and early January, but this strong eastward wind is replaced by westward wind on January 20 or 25. This means very strong southern warming event occurred in late January. This stratospheric southern warming event is generated by enhancement of stationary planetary wave from the troposphere. The polar night eastward jet is disturbed by planetary waves from the lower troposphere, and this strong eastward jet is replaced by westward wind during a stratospheric southern warming event. Stationary planetary wave from the troposphere is mainly excited by effect of mountain or land-sea contrast in the troposphere. Therefore, the amplitude of stationary planetary wave is much larger in the northern hemisphere than in southern hemisphere. This means the occurrence rate of southern stratospheric warming event is much higher in the northern hemisphere than in the southern hemisphere. This movie shows time evolution of weather map at 30-kilometer height in the northern hemisphere from January 1st to February 10, 2009. Red color indicate high pressure and blue color indicate low pressure. During early January, now SSW occurred. Early January, strong polar vortex associated with a strong eastward jet is located on the middle and high latitude, and this strong polar vortex is disturbed and elongated by planetary wave during mid-January, and after mid-January, this polar vortex is replaced by high pressure system. This means the pressure pattern changed drastically during the stratospheric southern warming event. Now, strong polar, this is very strong polar vortex. Early January, this polar vortex is distorted and replaced by high pressure system, and the stratospheric southern warming event occurred. So this means that polar stratospheric southern warming event is very drastic event in the stratosphere. This panel shows impact of 2009 stratospheric southern warming event on the ionosphere thermosphere system simulated by GAIA model. Left figure shows time height distribution of zonal wind at 60° north latitude simulated by GAIA. Strong eastward wind is replaced by westward wind on January 23. So this means the SSW event occurred on January 23. So this means GAIA can reproduce the 2009 SSW event. And upper right figure shows the time latitude distribution of semi-diurnal tide at 110 kilometer height. This is semi-diurnal tide in lower thermosphere. And lower left figure is a time latitude distribution of semi-diurnal component of electron density at 300 kilometer height. Semi-diurnal tide and the semi-diurnal component of electron density shows enhancement of semi-diurnal component during SSW event. This means SSW event influence the circulation in the thermosphere and ionosphere. Left figure shows the time latitude distribution of semi-diurnal tide amplitude at various height. So semi-diurnal tidal amplitude in the 27 kilometer height, 79 kilometer height, 116 kilometer height, and 378 kilometer height. This means that the semi-diurnal tide in the stratosphere, mesosphere, lower thermosphere, and upper thermosphere. And white line indicate occurrence date of southern stratosphere warming event. So this figure indicates that semi-diurnal tide is enhanced not only in the stratosphere, but also in the mesosphere and thermosphere. The semi-diurnal tide is amplified in the stratosphere during SSW event, and this enhanced semi-diurnal tide propagate into the mesosphere and thermosphere. So this means the SSW event affect tidal amplitude in the mesosphere and the thermosphere. And right figure is local time latitude distribution of E cross B drift during SSW event. So during the SSW event, semi-diurnal variation in E cross B drift is enhanced. This result indicates the enhanced semi-diurnal tide in the thermosphere produces this semi-diurnal variation in a eastward electric field and electron density distribution through E-region dynamic processes. This means SSW event is a stratospheric event, but SSW affects the circulation in the mesosphere, thermosphere, and ionosphere. So SSW is very important for the variability of thermosphere, ionosphere system. Next, we introduce impact of upward propagating gravity waves on the ionosphere, thermosphere system. Can you see this movie? Okay.
Yes. Okay.
This movie shows the temperature fluctuations at 400 kilometer height, simulated by high-resolution GAIA model. This simulation is conducted under solar minima and geomagnetically quiet condition. But we can see very many small-scale fluctuation of temperature at 400 kilometer height. And the horizontal resolution of this result is horizontal resolution is 0.5 degrees longitude by 0.5 degrees latitude. So it's a very high resolution model. We can see many small-scale fluctuations of temperature. Of course, high temperature is located during daytime, and low temperature is located in nighttime. But there are many small-scale fluctuations. This is a solar minimum and geomagnetic quiet condition. So these small-scale fluctuations are mainly caused by gravity waves from the lower atmosphere. So these fluctuations are due to upward propagating gravity waves. So next we show some gravity wave behavior. Left figure is a time height distribution of short period zonal wind fluctuations. This is a short period component of zonal wind variations. And the phase line of this small scale short period fluctuation descends with time. This structure indicates upward propagation of gravity waves. And right figure, longitude time distribution of zonal wind fluctuations. Some fluctuation of zonal wind moves westward, other fluctuation moves eastward. And the amplitude of zonal wind fluctuations exceeds about 50 meters per second. So this means that the fluctuation of zonal wind component due to gravity waves are very important for thermospheric circulation. Next, we show impact of gravity waves on the ionosphere. Left figure is a local time height distribution of electron density at 35 degrees north latitude and 140 degrees east latitude. This is electron density distribution near Tokyo. Of course, electron density have a clear diurnal variation, but the peak height of electron density ranges from 240 kilometers and 280 kilometers. There are some fluctuation of peak height. And the period of fluctuation ranges from 30 minutes to 2 hours. Upper right figure shows the local time height distribution of short period variation of electron density. The phase line of this short period variation descends with time. This structure is similar to the structure of upward propagating gravity wave in the neutral atmosphere. So this means that this short period fluctuation of electron density is caused by gravity waves. And the right lower figure shows electron density fluctuation observed by receivable radar. The simulated structure of short period variation is quite similar to the observed structure of electron density variation. And further analysis, further detailed analysis detailed that these fluctuations are caused by neutral wind field fluctuations associated with gravity waves. This is described in 2018 GAGR paper by Miyoshi. This movie shows a short period variation in the total electron content near Japan. This is longitude, latitude distribution of TEC variation, a short period component of TEC variation near Japan. Local time is shown here, and this is a variation during daytime. This TEC variation moves southward during daytime. These are due to MSTID or LSTID during daytime. So this means GAIA can simulate daytime MSTID or LSTID. Our analysis indicates this TID are generated by gravity waves propagating from below. In this simulation, we also assume solar minimum and solar geomagnetically quiet condition, but we can see this clear MSTID that propagate from northward to southward. So this TID is generated by gravity waves from the lower atmosphere. So this is my summary. There are many important phenomena in the ionosphere thermosphere system caused by atmospheric waves, but there are many unsolved topics in the ionosphere thermosphere system. Now, the vertical coupling processes by atmospheric waves from the lower atmosphere is one of the hottest topics in the Earth science. Thank you very much for your attention.
Thank you, Dr. Miyoshi, for this very nice presentation. Now, I think we have time for questions. Now, I'm opening for questions. Please, if someone has questions to Dr. Miyoshi, you are free to do.
Fábio.
Oi.
Professor Miyoshi, thank you so much for your presentation. Congratulations for conducting this research using GAIA model. There are a lot of interesting results that we can see that you can explain several phenomena in the atmosphere. When you start your presentation, you show some maps of wind and temperature, the variability of the wind and temperature in different altitudes of the atmosphere. And one of them that is at 110 kilometers, I could observe that there are a lot of variations compared to the other altitude. May you comment what the physical process that are causing this kind of variation?
Oh, this picture? Oh. This picture?
It's coming, yeah.
Yes.
Yeah.
In the troposphere, the barometric wave is dominant in mid latitude. So this barometric wave is associated with eastward moving low and high pressure system. It's a weather system in the troposphere. In the stratosphere, stationary planetary wave is dominant. So this zonal wave number one component is dominant in the stratosphere. This is a wave pattern. This wave pattern is generated by stationary planetary wave in the stratosphere. Yes. In the mesosphere, it is not clear, but we can see very small scale structure. So this small scale structure is due to gravity waves. This is snapshot, so very chaotic. We can see chaotic signature in the mesosphere. This is due to gravity waves. Yes.
Okay, thank you.
Oh, Fabio, can I ask a question?
Yes.
Oh, I am sorry, Ricardo. My microphone was off. Yes, please. You can make a question.
Hi, Professor Miyoshi. Thank you very much for your good presentation. I have some question about gravity waves that I'm not sure very well, but one of the figures you present may be the temperature at 400 kilometers. We could see that there is some effect of gravity waves at that height. Is it possible we detect gravity waves at 400 kilometers? If so, how could we do that?
Yes.
Yeah.
This is mainly due to gravity waves from lower atmosphere. Yes.
Okay, this is a simulation, right?
Yes, yes.
Suppose that I would like to observe by instruments. So, do you have an idea how we could do that?
But this is simulation result, but there are no observations in the upper atmosphere.
But suppose
yes,
that
very difficult.
Okay. So in the opposite side, we have, for example, at 8 kilometers, the first figure that you have showed. I think in our area, there is a problem, maybe, I don't know why in advance, but we can observe gravity waves easily in the mesosphere.
Yes.
But we never mention gravity waves in the troposphere. I don't know this is if it's a fault of our area.
Yes.
But if they are, okay, suppose that gravity waves is the source, the main source is in the troposphere.
Yeah.
We never mention, we never make an observation, any study about it. Maybe in the meteorologists do that, but we never mention it. And this is, I think this is a fault of us. What do you think about it, please?
It's a very difficult question.
I understand.
Yeah.
I understand.
Yeah.
Okay, that's okay.
Okay.
We have two questions from the QA box.
Igor.
Okay.
Let me ask the question from Cosme. He asking in YouTube. Cosme asked Mr. Miyoshi if GAIA can simulate the effects of midnight temperature maximum.
Yes. GAIA can simulate midnight temperature maximum. Yes.
Okay, thank you. We have two questions in the Q&A. We have time, I think. There is one question from Caio Martins. He asks Professor Miyoshi, what are exactly gravity waves? I think this is a common doubt.
Oh.
Professor Miyoshi, can you hear me?
Yes. Your question is this. Your question is this is gravity. Is this a gravity wave or not? You mentioned.
Yeah, it's a question from the audience. The Caio Marques is asking what are gravity waves.
What is exactly the gravity? What exactly gravity wave? Yes, this yes, I analyze phase structure or phase structure between wind and temperature. So we check this is gravity wave. Yes.
There is we have more. We still have time to question. There is a question from that I can. Let me ask if you can see the Q&A. There is another question here that I can't identify from who make the question.
Can I read it?
La Nina. Oh, La Nina. You. Another question is the effect of La Nina.
Yes.
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 Yes. Of course, the El Nino and La Nina affect cloud distribution in the troposphere. So this means that excitation source of tides are influenced by El Nino and La Nina. So this means that tidal activity is influenced by El Nino and La Nina. So this modulation of tides affect thermosphere and mesosphere. This is possible effect. Yes.
Okay. Thank you, Professor Miyoshi. We are out of time. There are more questions here that I think you can answer to the person. I'd like to thank you again for this.
Thank you very much.
Very nice
Rabiu.
presentation.
Yes. See you later.
See you.
Thank you. See you again. Yes.
Thank you. Let's move to our next speaker. Now, our next speaker is Dr. Amitava Guharay from Physical Research Laboratory in India. Dr. Guharay is an associate professor at Space and Atmospheric Science divisions, as I said, in the Physical Research Laboratory in India. Amitava, thank you for attending and for give us a talk.
Yeah, am I audible?
Yes.
Yes.
Okay, let me share. Is it visible? Screen?
Yes.
Yes. You have about 25 minutes. Let's.
Okay, I'll try to maintain. Yeah. Yeah. Good morning, good afternoon, and good evening in the respective local time zones. So, and I'm very much thankful for giving me this opportunity to present this work here. It's my pleasure to be a participant of this program. So today what I'm going to do, I'll just talk about some recent result about intraseasonal oscillation in the equatorial middle atmosphere. So please, can you see my pointer?
Yes.
Yeah, pointer you can. Okay, thank you. Yeah, so this work is done in collaboration with Batista, PP Batista from INPE, Brazil, and R.A. Guharay from UFCG, Brazil. So the main broad category, if you see in the atmospheric waves and oscillations, that is the highest frequency waves of minimum period, that is the gravity waves. You already heard a lot about from Dr. Miyoshi in the last presentation. And then the tide comes, that is the bigger period. Here in gravity wave you see minute to hours. Then tides are having harmonic of day, that is 24, 12, 8 hours, 6 hours, and so on. And the planetary waves comes hereafter around roughly period of 2 to 20 days. And then come the intraseasonal oscillation that today I'm going to talk about this result of regarding this intraseasonal oscillations. That is roughly around 20 to 100 or 110 days. And the seasonal oscillations are the maximum period. And those comes with the annual oscillations. That is around 12 months, 6 months, 4 months, and something like that, so on. So before I go to the details of the result, I just want to show the source region of this intraseasonal oscillation. So the intraseasonal oscillations is as a result of ocean and atmospheric coupling. You know, ocean and atmosphere, both these regions are highly coupled, one affect another, and there are several feedback mechanisms which is happening. So that way, ocean is affecting our atmosphere, and atmosphere is affecting the ocean. The one important thing due to the ocean heating we see in the effect in the atmosphere is the convection. And you can see the left figure here that this is a very high temperature zone in this region. That is the Western Pacific and Indian Ocean region. Let's see. And the summertime mean temperature generally remains well above 28 degree Kelvin, 28 degrees centigrade. Sorry, it's a mistake. So it remains more than 28 degrees centigrade in the summertime in this region. And due to this, there is a very high convective activities goes on. So this region is very much active in convection. Okay, and also convective anomalies are present there. I mean the difference in the convection pattern. So due to that, this in lower atmosphere, the Madden-Julian oscillation, meteorologists it's a more common term, that is generated here due to this convective anomaly, and that propagates generally in the eastward direction from western to east Pacific region. And the imprint of that oscillation you see in the middle, in the higher atmosphere, that is in the middle atmosphere, that is intraseasonal oscillations you see. So what you see, this is one showing how it is evolving with time. You see, as it is generating in the Indian Ocean, this convective pattern, and it is shifting towards right, eastward, first week, then second to third week, and then you can see fourth to fifth week, it has almost reached Central Pacific and Eastern Pacific region. The thing is that its phase speed is very small compared to the waves and tides, other atmospheric features. It is around 5 meters per second. So what happens? As it is the feature, it goes up. Basically, as I said, due to this low phase speed, they directly cannot go upward. Okay. So what they do, this change in convective pattern, they changes the waves or tides. Those are affected by the convection in the lower atmosphere. So they affect those waves and tides, and as those tides goes upward, they carry this feature. So what is happening? These oscillations, they themselves cannot propagate directly upward. So they take the help of these waves and tides. So waves and tides carry this imprint of these oscillations, they propagate. And as they dissipate in the high altitude, you see the imprint on the intraseasonal oscillations. So basically it is the modulation of the waves and tides in the atmosphere by this intraseasonal periodicity. So what are the characteristics? As I already explained, that due to the convective anomaly in the Indian Ocean region, they are generating and they propagate then eastward, and their phase speed is low, so they take help of waves. They get generally they modulate the waves in the atmosphere in the periods, the longer period, and these waves carry this signature to the higher atmosphere. So now come to the result. That's what I we obtained. This is the observations from meteor radar from Cariri, that is the equatorial latitude in the southern hemisphere, Brazil. It's an observation during 2008. Here you are seeing the altitude, and this is the period. That is basically a periodogram, Lomskarvel periodogram. So here you can see in the zonal wind, a very clear feature of this intraseasonal oscillations at a higher period, around mostly 30 to around 60 to 70 days of periodicity that is present there. So you can see there are basically two band. One is here 30 to 32 days, okay, and another is 45 to 70. They said, and meridional wind doesn't show that much strong feature. It is a property of the intraseasonal oscillations that they dominate are present in the zonal wind. So now this is the wavelet spectrum at different altitude in the mesosphere and lower thermosphere region, starting from 90, 87, 84, and 81 kilometer altitude means. And the wavelet is basically showing the periodicity present and how they're evolving with the time. So this is the whole year time span for all the plots. And you can see that one period is present here near about year 50-day period. So, and that is present in all other altitude also. But one thing is that that is shifting in time. You can see. So there is a kind of downward shifting of this periodicity, the phase of the wave. You can see. So overall, a 40 to 70 days period band that is very clear in this plot during this initial 100 or 120 days. This is very dominant, and the central peak, that is the central peak of this period, that moves from 45 to 6 days as it comes from top to bottom. So period is changing a little bit. And the shift of band center from 50 day of the year, you can see, as I have said, that with time it is propagating downward. So at lower altitude, you are seeing it later. So if you calculate the vertical phase speed from this, you can see it's approximately 225 meter per day. Next, we have tried to see now, for last one we have seen in the MLT its feature, that intraseasonal oscillation feature in the MLT. Now we're trying to see in the other parameters in lower atmosphere. So one is the Wheeler. This is basically proxy of the convective activity, because as I said, convection is the most important factor. It is causing this kind of oscillation in the lower atmosphere. And next is the total column water vapor. And this is the U wind, that is the zonal wind, that is eastward positive, around 150 millibar and 10 millibar. So this is showing Wheeler around, this is also showing a period around 30 to 40 days. Okay. So there is an influence of convective activity. It is confirming. And this water vapor also showing around 50 to 60 days periodicity. So that may probably indicating the influence of tides. Probably tide is carrying this feature in this region. And small peaks of period less than 20 days are also present, you can see in some cases. Those are due to possibly Rossby or Kelvinoids that we are not going to discuss in this talk today. And the other two altitudes are lower atmospheric altitudes or regions are also showing in this band periodicity. So the thing is that there is a good correspondence between the of this ISO period, the period we have seen, that is with the MLT in the last slide we have seen. So there is some kind of relation. I mean, common thing is there in the MLT and the low atmospheric parameters in terms of this intraseasonal oscillation. So this is showing the filtered wind. One is zonal wind, that is one in MLT region, mesosphere and lower thermosphere, 80 to 100 kilometer, and next is the troposphere and stratosphere region, that is starting from ground to up to 50 kilometer. So you can see that this oscillation feature that is intensified earlier, and it is slowly reducing with time, and there is it's a downward showing propagation, and rest of the time it's not so dominant. And then in the lower atmosphere, you can see that there is an intensification of these intraseasonal oscillations to altitude mainly. Suppose it is above 40 kilometer, 40 to 50, and another near 10 or 15 kilometer. But in between, there is no intensification of this. So this is probably indicating that is a refraction, because the waves, those are carrying the intraseasonal oscillations from the lower to the atmosphere, they are not directly propagating in this region from low to high. Rather, they are refracting, okay, due to the atmospheric wind condition. They are refracting and going to the high southern latitude, and then again coming back to the higher altitude to the low latitude. So this is probably due to the refraction. We'll see later more on this result. Now we have tried to see this relationship among these different interseasonal features in different parameters. So like one wind is taken, zonal wind around 81 kilometer. So this is basically a filtered wind, 20 to 110 days. All are filtered here, and trying to see what is the common features among them. And you can see there's a less consistency among various parameters. Sometimes is observed, not always. Sometimes it is good, sometimes it is not good correspondence between these two. So this is possibly due to the contributing waves. Basically, the waves, those are carrying this feature, their property may be changing with the altitude. So because of that, you can see that and also the difference in the phase. If there is change in periodicity of the contributing waves, you will see this effect in the phase pattern also. So because of that, probably there is a mismatch sometimes. And lower one is showing the initial 1 to 150 day of the year, when this intraseasonal activity is very high. That time is chosen, and this cross correlation is found just to see the exact relationship between these parameters, like wind at 81 kilometer and Whaler, that is a convection, and wind with the water vapor, that is representing tide, and wind and the lower atmospheric wind also. So maximum correlation is very good, 0.79. High correlation is found between this this water vapor and this wind at MLT. So probably tide is linked with this. I mean, tide is contributing, and also we are getting good correlation with surface wind also. And now here he trying to see this mesospheric height, this intraseasonal feature, how they're relating at different altitude in the mesosphere. They're relating with the other, I mean, in lower atmospheric, I mean, in troposphere and stratospheric, same ISO feature. So the ISO in the mesosphere and lower atmosphere, and ISO in the troposphere stratosphere, how they are relating. So they are at each altitude in this observed data at each altitude. This correlation has been calculated, and you can see these four colors are representing four altitudes in the mesosphere, and in the troposphere stratosphere, whole altitude is considered, starting from ground up to 50 kilometer. And you can see there are some alternate kind of these correlation values, like some maxima, some minima is coming. If you see the vertical scale, that comes around 10 to 15 kilometer, some scale, probably vertical wavelength of 10 to 15 kilometer waves which are having, probably they are dominant in this effect of the ISO. Another point is that the maximum correlation with this mesospheric wind or mesospheric ISO, that is coming around very low, near ground, near ground, that is very low altitude, below 4 kilometer. So probably it is indicating a source in the lower troposphere. Now to see its longitudinal propagation with time of the year, and we have done this filtering analysis. We have done filtering for considering wave number for the I mean, longer period wave, considering 1 to 6 wave number. This is in convection, that is Euler, and this is in the wind, around 10 meter near ground. And both of the plot, we can see that near 60 to 120 degree east, that is near Indian Ocean and West Pacific region, there it is very strong and it is propagating eastward. So from this plot, you can estimate the phase profile because you have time information and the longitude. It comes around 5 meters per second, this speed. And this is the longitude of our observation place, in the present observation place. So here you can see that they're propagating from this longitude to the higher longitude. So probably the ISO features we are seeing here that is caused by this eastward propagation of this ISO that is generated in the Indian Ocean region. So this is to see this ISO effect on the tide. So this periodogram has been estimated from this daily tidal amplitude at different altitude for diurnal, semidiurnal, and tardinal. And this periodogram clearly shows some periods. One is in lower period, less than 20, probably. This is the other planetary waves features. But the thing is that here, around longer period, that is the interest of intraseasonal oscillations, you can see modulations like 30 days, here 50 to 60 days. And in tardinal case, although it is not very strong like diurnal, semidiurnal, but still some periodicity is there. So now to see the wind condition, because the features of these intraseasonal oscillations in the atmosphere, what we see that I have discussed, that this is due to this dissipation of these waves at certain altitudes. Those waves are basically carrying the intraseasonal oscillation feature. So as they dissipate, that feature reappears. So to see whether wind is helping them to dissipate or not. So as we have seen, the zonal wind here in westward direction in the MLT region. So eastward waves are favorably can go upward here in the MLT region. But in the troposphere and stratosphere region, you can see one altitude near 10 to 15 kilometer, it is coming to be eastward. And then it is mostly in the westward. Okay. So in this altitude, there is a possibility of dissipation of the eastward waves. Probably because of that, at this altitude, we have seen some enhancement of the intraseasonal oscillation activity. So the summary is that the prominent ISO signature is observed during the initial time of the year in this period band, 40 to 70 days. And in the lower thermosphere, the dominant ISO is observed in the period band 30 to 60 days in both convective activity and in the water vapor. So, and considerably high correlation has been observed between MLT and the lower thermosphere region, indicating the significant dynamical coupling between this region, lower and middle atmosphere. And in the ISO in the MLT shows downward phase propagation of the peak amplitude, indicating a role of dissipating upward propagating waves for this imprint here. And the eastward propagating waves and tides are probably communicating this ISO signature from the lower to the MLT region. And the origin of this MLT ISO will to be placed in lower troposphere. You have seen from the high correlation value near ground. And this is, and in the from the filter analysis, we have seen that the dominant, the source region is the Indian Ocean and the Western Pacific region. Now I'm quickly going to the second result. It's basically comparison between two locations. But one is around equatorial region, Caridi, and another is Cassiopeia Paulista, that is in subtropic region in the southern hemisphere. So total observations around 796 days done, and you can see this U wind basically, and this is the zonal wind and the meridional wind over both the regions, and you can see this higher period features are present in both the locations. So now we are trying to compare these two locations, features of the interseasonal oscillations in these two locations. So this is basically filtered data in the 2200 days filtered data. So this is just for comparison at different altitude. You can see good comparisons are observed most of the time, and sometimes they are not matching. So there is some common contribution of ISO. Common kind of waves are present in these two locations. Can be said because of this coherence in between these two locations, and sometimes less coherence is also present. That is probably due to the latitudinal variability of the wave dynamics. Now to see this ISO feature, that is intraseasonal oscillation feature, in the convection activity, this Euler data is plotted. You can see that the zone near this place, this is the zone. There are certain times there is this Euler value is quite low, indicating very high convection in this region. So that is probably that is helping these ISO features that is observed in the MLT region over the locations. So this is periodogram in the wind about both the locations. You can see the periods, high periods are present at several periodicity in this range, intraseasonal range, and oscillations is also getting higher as you go to the higher altitude, like as you go from 150 HP to 1 HP, this oscillation amplitude is also increasing. So if you compare now this interseasonal oscillation in the MLT region with the convection activity in the lower atmosphere, like past we have seen for the other observations, sometimes we are getting good coherence in some span, and in-phase behavior is found between this zonal wind and the Euler. That means one is in the mesosphere and lower thermosphere, and one in the lower atmosphere convective activity. So what it says that varying ISO characteristics with altitude. So with altitude, the ISO characteristics is also varying, probably due to the propagating waves, those which are carrying these features, they are changing. Because of that, some altitudinal variation is observed. Now this is showing correlation. This is around wind 90 kilometer Euler, and this is 1 HP height 150. So it's basically comparison between the two locations. One I have said subtropical region, and one is in the equatorial region. So how they're matching, or what is the relation? So it is seen sometimes 0.6 correlation coefficient is found at the high altitude, and lower altitude it's a little bit less. So MLT, the ISO feature in the MLT is this good correlation between these two, better in compared to the lower atmosphere is found. So the probably due to this commonness of the waves at the high altitude. So now this is the filtered profile, vertical filtered profile, and both the places, zonal wind. This is troposphere and stratosphere, and this is in the mesosphere. You can see these features. So what we see, two evident high amplitude regions near upper troposphere and stratosphere. You can see, although mesosphere there is not very consistent behavior found out, but in the lower atmosphere you can see two regions, one around 18 to 60 kilometer, another above in the near stratopause 40 to 48 kilometer. So this is again indicating that probably the refraction of the waves carrying these features, ISO features, they are reflecting through the mid latitude and coming back to the low latitude at the high altitude. And another thing is that in over this location, Caridi, one annual oscillations kind of thing you can also see in the height of this ISO feature over this region. That is very prominent. Although it is present, it's not that clear like the Caridi. Okay. So, so the summary is the prominent ISO activity has been found in this region in this period band of this intracellular oscillation. Significant internal variability is also observed. Now, correlation between the mesosphere and the low atmosphere is found to be a little bit higher in case of Cassata paulista and Caridi. And MLT, ISO in the MLT2 station show better correlation in the MLT region compared to the lower atmosphere. And most prominent ISO amplitude, the upper troposphere and stratosphere, that is the reflection, and annual oscillations as discussed. So I think I will stop here, and thank you for your attention.
Thank you, Amitava, for this nice talk. We have time for 1 or 2 quick questions.
Yeah.
Has anyone have questions?
Fabio, yes, I have a quick question, a curiosity. Amitava, is the intraseasonal oscillation related to the made in Julia oscillation, the troposphere?
Yes. Yeah, they are related. Yeah, Madden-Julian oscillation is the, one of the most dominant contributor of these interseasonal oscillations. Yeah, as I said, they are mainly created or excited in the lower atmosphere due to this high convective activity and high temperature over the ocean. So definitely they have relations. And the MJO is, you can say, one part of this interseasonal oscillations. Yeah, dominant part. Yeah.
Okay, thank you.
Hello.
Dr. Sivakandan, do you have a question?
Yes, it is nice presentation. Is there any delay between tropospheric ISO and MLT region ISO? The number of days. Suppose I am seeing January in the troposphere or February in the MLT, are they occurring simultaneously?
If you see in the scale of periodicity, like 20 to 100 days are considering. In this periodicity range, if you consider, you won't say a very large difference. Okay, few days you can say difference between the lower atmospheric and the higher atmospheric, this ISO. Okay, it can go up to 10 days or even more, this difference. Okay, this peak. Yeah.
Thank you.
Yeah, sometimes you'll see.
Thank you, Amitava. Thank you again for your nice presentation.
Thank you.
I think we can move to the next speaker. Our next speaker is Dr. Babatunde Rabiu from the Center for Atmospheric Research of the Nigerian National Space Research and Development Agency. Thank you, Dr. Rabiu.
Thank you very much. Thank you for that, Fabio, for the introduction. And I have a short time to do a presentation this morning for you in Brazil and afternoon in Nigeria. And so I will be quick with my presentation. Is to show the status of space weather science in Africa, and also to present what we have as network of ground observations, to give information about the facilities that we have on ground to monitor the space weather, of course the ionosphere, and to present some scientific results and how we collaborate among ourselves. Africa straight I'll go to the presentation. By the way, I want to thank the organizers of this conference for allowing me to share our situation in Africa and the progress we're making, and to share the probable opportunities for collaboration with others, scientists from different parts of the world, especially in Brazil. Africa is a big continent of 54 sovereign nations, each nation having its own constitutions and set of governments, with a very big landmass of 30.2 million square kilometers and a very heavy population of 1.248 billion people, which is like almost 16%, more than 16% of the total world population. And the interesting news for us is that more than half of these 54 sovereign nations are now involved in space weather studies. And space weather is fast becoming a new enterprise also in Africa. The map of Africa is shown here with the Nigeria in green color, which is where I am speaking from. I want to speak about the uniqueness of space weather over Africa, as for emphasis sake. Africa is unique in terms of space weather studies because it offers a very large landmass to study the behavior of the equatorial region, that is the equatorial ionosphere. And this is because the magnetic equator over Africa is of the broadest range, from western coast of the Senegalese coast to the other coast around Ethiopia and co. We have a very broad range there, broader than elsewhere, where you can study the equator. I mean, you can study the processes around the magnetic equator. As also the equatorial ionospheric anomaly has the widest width. In terms of the width, it can be studied in its full spectrum using ground-based facilities. Yes, we are conscious that some of this portion is made up of deserts, especially in the northern hemisphere. But at the same time, we have regions where we can actually study this. And that was what informed the Kyushu University under then Professor Yumoto to put some magnetometers along the 96 magnetic meridian chain, which run from somewhere in Egypt down through the East Africa to South Africa. And big database is still available with the International Center for Space Weather Science and Education in the Kyushu University, at Kyushu University. Now, again, I want to emphasize on the nature of the geometry of the magnetic equator, which is also very important in studying the equatorial ionospheric processes, in the sense that over Africa, the magnetic equator is almost horizontal, though not horizontal, but then the inclination is not as heavy or as high as the one in South America. This clearly explains why the equatorial processes are quite different. At times, they are quite different from each other when you want to compare processes, ionospheric processes within the equatorial regions in South America and from that of the over Africa. In some other parts of the world, the magnetic equator passes through the deep, the tip of the continent. So they are mostly on highlands and oceans, and that makes it more complex to study equatorial processes. So in terms of instrumentations, Africa had a big problem some time ago, but since 2004, when the International Geophysical Year was launched by the United Nations Office for Outer Space Affairs in collaboration with NASA and European space agencies, some equipment started coming to Africa for ground observations. And that was when we started having magnetometers, GNSS receivers, and some other facilities that have come in now. The IHY was preceded by the International Space Weather Initiative. And after that, there have been some other initiatives by some small groups or international groups. And the summary is that we've been able to have a number of equipments on ground to monitor the ionosphere in Africa, such as magnetometers, GNSS receivers, or sky optical imager, the FPI, the fabric parrot interferometer. We have some digisons in Africa, in Nigeria, in Kenya, and Ethiopia. And then we have this Callisto, which is an IHY equipment also, and several sudden ionospheric disturbances monitors that have been deployed in different locations. And also the program has enabled us to develop our capacity in Africa for space weather science. And now we have intracontinental training of our graduate students with 1 or 2 countries working together to train their graduate students, and we have which collaborations among African scientists. We do organize series of space weather schools as well. This map is just showing some of the equipment that are available in Africa at different locations. The distribution, this is not really detailed enough because some are not captured, but then, so now we have equipments in different parts of Africa, unlike before. And like I said, there are many, we have quite a number of African professors that we work together in the space weather studies. And we also have diligent students, vibrant students that are very intelligent and that are ready to work with us. And we have research facilities that we can use to do internationally competitive research. Now, in terms of instruments, it has been mainly by foreign intervention, but nowadays we have increase in national participation that different countries are coming up to support space weather science in Africa. I know of South Africa, Nigeria, Kenya, and some other African countries are also joining this to move the study of space weather science forward. This is a typical laboratory, which is like an observatory of our own Center for Atmospheric Research, which is located in Abuja. And this building was erected in 2015. And then there we have the only optical imager in Nigeria and for now in Africa that is functional. And this can capture up to 500, because the fish eye field is about 500 kilometers radius. So, and we have 2 magnetometers domiciled in this location as well. And we have a GNSS space weather monitor there. And at the moment, we are also monitoring the ionosphere using a low-cost GNSS, a dual frequency GNSS receiver. We've been able to organize many schools and workshops and training, as well as conferences in Africa, right from 2006, that I've been personally involved in most of this, from Cape Verde. This was in Cape Town in 2006, and Ethiopia. We continue to run all these schools over Africa in different locations, really. And the latest was the online fashion, which we took advantage of the COVID-19 lockdown to run our international colloquium on equatorial and low latitude ionosphere, which is now a yearly program that we run and to study the equatorial and low latitude ionosphere. And the lecture notes for this particular colloquium and the papers that were presented is available at this web page. at this web page, someone can get the link and download the lecture notes and the resources that were presented by various resource persons at the meeting. This is just a typical picture of our school that was held in 2015. That's 5 years ago. This was the first school we had in this series. Before we had 2 other schools, then we migrated to a colloquium in 2018. We migrated to a colloquium, and since then we've sustained the colloquium on a yearly basis. Now, to show some of the results, because I know I have like 12 minutes to speak, the African scientists, like I said, have continued to publish in various journals. Now, look, using the data that I mentioned, the network, the magnetometer network of Kyushu University, of the International Center for Space Weather Education and Science, we had a couple of magnetometers, about 11, along this 96-degree magnetic meridian from Egypt through East Africa to South Africa to Amanos. The longitudinal difference is not so much, so it's approximately 96-degree magnetic meridian. And there, we use that to study the solar quiet variation in Ish. This is presented for Ish, and on the left axis is the geomagnetic latitude of those different stations. And then we have these across the season, this season, March season, J season, and September equinox. Obviously, around the magnetic equator at the low latitude, close to magnetic equator, is where we have the greatest values of SQH across all the seasons. And of course, this is due to the equatorial electric jet effect. And then we observe that we have the maximum effect during the autumn, that is during the September equinox. So in this work, the seasonal variation of SQH was discussed, as well as the spatial variability of the SQ across the magnetic meridian. This is published in this paper by Ross Balaji et al. 2015 and can be assessed as well. Another study I want to talk about is the study on the equatorial electric jet. And we took advantage again of the same database, since that was the first time we were really having such facilities on ground in Africa, to look at the equatorial electric jet in the eastern axis as well as the western axis. Along the western axis, we picked the stations that are represented by these geomagnetic, by these values and their geomagnetic latitudes. We consider Ilorin as a station because it's at minus 1.82 degrees, while Addis Ababa is 0.18. So this is between plus or minus 3 of the magnetic latitudes, equator. So the implication is that these two locations, Ilorin and Addis Ababa is on the east, and Ilorin on the west fall within the equatorial electric jet region. We estimated equatorial electric jet for these two stations, and it was revealed for the first time clearly that the Western African equatorial electric jet tends to be weaker. It tends to be weaker than the Eastern equatorial electric jet. So that's what we got. In the line plots here, we have this. The cross line shows that of the Western electric jet, while the plain line shows that of the Eastern electric jet. The discrepancy was somehow attributed to a process of reinjection of energy in the jet as it flows eastward. This west-east asymmetrical behavior in the equatorial electric jet in the African sector is further confirmed by some other works that we did, which I think I'll show in the next slide. And that of Yusengo, that's Endawoki and his group, use another set of array of magnetometers, which we call AMBER. And this is what they got is the plot, the contours on the lower portion of this screen. 7.6 degree east is the one is in Cameroon area, and that's the location that Abuja. They use Abuja data because we have AMBER system there in Abuja. And then 38.8 degrees is in Ethiopia. That's on the eastern axis. And looking at this, you could see that the electrojet that is estimated in the eastern axis, when you look at the scale bar, is greater than that of the western axis. This also shows that, it shows the longitudinal variation. I just want to talk more on that of the African stuff. We have Ilorin here, and then we have Addis Ababa here. You could see, if you look at the scale bar, you see again that is greater in the eastern than this of the western axis. Of course, there's longitudinal variation of equatorial electrojet. In the Okayo SCB is the greatest equatorial electrojet, and we've had explanation for this because the observation there has been so much. Also, we have variability of the counter electrojet also, and even the afternoon counter electrojet. These have been looking at the occurrences of these different electrojets, counter electrojets, and we have results to show for this, and this has been published in different papers that are also, I think some of them are open access. We somehow concluded in one of the works that the activities that support strong equatorial electrojet do inhibit occurrence of counter electrojet. I still want to show some other things. This is a work from Ouagadougou and in Burkina Faso using ionosphere data that is available for a long time. And this is from 1966 to 1998. The ionosphere is no more working, but the database is available. It's being kept by an organization in France, and we got the data, and we use this to study the nighttime plasma drift over the region. And we got a remarkable feature that shows the consistent local pre-sunrise drift enhancement for 2 solar cycles. And 20, these are 20 and 21. You have this effect here. And we discovered also that the rate of inhibition of scintillation effect increases with decreasing phase of sunspot activity and maximizes during the solstices, among other results. This one is interesting to us because this is the first time that I will report occurrence of plasma bubbles over Africa. And it's been published in the JGR paper, Oko et al. 2017. This is a collaboration with the Institute for Space, Earth, and Environment of Nagoya University that brought the optical imager to Nigeria. So the oil sky imager sits in Abuja at the center here of this map, and has 500 kilometer radius everywhere, where we found that most of the plasma bubble occurrence occurs about the midnight. And of course, for our location is maximum in the midnight, at the midnight, and then begin to go down. But it's not asymmetry about the midnight, the distributions. That is it. And and you can see the capsule. That was the camera is capturing. That's the plasma bubble moving at times. It's not all the time this occurs. And we also discovered that it demonstrates equinoctial maximum with a kind of asymmetry as well. It's more in March equinox and then than the September equinox. And this also aligns with the DMSP satellite stuff that were obtained sometimes ago when you have the equinoctial maximum. This is in Africa. The left wing on the plot is showing that of the African region, and you can see that it demonstrates the equinoctial maxima too on that plot. And we've been able to capture this using ground data. We compare our results with, we use GNSS data also, and we follow some existing methodologies to obtain plasma bubble signatures from GNSS data. And we have some results that are quite similar. On top here is the hair glow data, and under it is the GNSS data that we use to estimate the percentage plasma bubble occurrence. And I think this will be the final one, and to show on this result, recently we started working on the AfriTech model, a model to use GNSS data to generate tech over Africa, and it's a neural network based model, an artificial neural network. And on this, we're able to get this model, which is freely available at this web page, and it's still be published. The work has been published we've published some works on this in the space weather in JGR, because initially we had a quiet condition, and recently we're able to do that of the disturbed conditions. We work with our colleagues from the South African Space Agency to upgrade the model. For example, what you see there, this is for 17th, for today. And we got this for today, so you can use this for prediction, and it captures the equatorial anomaly so well. This is for today, and this is for tomorrow as well. And then over Africa, it gives a good capture, it captures the procedure in the ionosphere so well. And we use this also at the time this was in JGR, we use this to discuss the variability of the EIA over Africa, because from this plot, when it's captured, you take the profile at different longitudes, and then we can get, using the spatial maps, we can determine the positions of the crest and the trough, and we study the variability as well.
Dr. Rabiu, I think we are out of time.
Okay. All right, thank you very much. I think I will stop on this, but I will show you that we're at the moment working on the equivalent of a super dam in low latitude with the Virginia Tech University, and the items have started arriving, and this will be in Nigeria, and we hope that it will enhance our research capability. Thank you very much.
Thank you for your presentation.
Yes.
We have one question from the YouTube. It's a quick question. Diego is asking about the data availability.
Yes,
it's possible to access this data if it's possible, of course.
Yeah, it's possible to access the data, and for data, it's possible to access all the data that I've mentioned in here. My web page is here, is shown on this presentation, and then when the papers that are published, we disclose. There is a disclosure on the data. So some of these data are already available online, and appropriate acknowledgement is demanded from the users. So the data is available for research purpose. Yes.
Thank you again. Let's move to the next speaker.
There is a question in the Q&A box. I will ask to.
I'm sorry, I didn't see.
No, we can answer offline to Dr. Batista.
Yes, a question from Dr. Inez. Okay, so we are going. We can move to the next speaker. Our next speaker is Dr. Mani Sivakandan. from Leibniz Institute of Atmospheric Physics in Germany. Thank you, Dr. Sivakandan. You have about 12 minutes for your presentation.
Thank you. Can you able to see my screen?
Yes.
Yes.
Yes, yes. I'll see your screen.
Thank you for the wonderful opportunity. I thank Professor Igo Paulino and other local organizing members for providing this opportunity. So today I am going to talk about the comparison of seasonal and longitudinal variation of daytime MSTD activity using GPS observation and GAIA model simulation. And in the first talk, Professor Miyoshi explained about the GAIA model simulation and its capability. Here we done an exercise to compare whether the GAIA model is capable enough to reproduce the daytime MSTD activities which are occurring in the ionosphere. And for that observation, we use the GPS TEC data. So medium scale traveling ionospheric disturbances are wave-like fluctuation in the ionosphere electron density, which are having the horizontal wavelength from few hundred kilometers to 1,000 kilometers. As far as the generation mechanism concerned, there are two main generation mechanisms so far. One is the gravity waves, which is mostly generated in the lower atmosphere, or this also can be generated in the middle atmosphere. Let us consider 80 to 100 kilometers, and these waves can propagate into the ionosphere, and then they can undulate the ionospheric electron density, then lead to the MSTID generation. And this is the mechanism which believed to be the main causative mechanism for the daytime MSTIDs. And there is another mechanism which is called the Perkins stability mechanism. This is associated with the electric field perturbation in the mid-latitude ionosphere. Whenever there is a change in the meridional wind and eastward electric field, it can destabilize the mid-latitude ionosphere. So it can lead to the Perkins instability. Then it can generate the electric field associated medium-scale traveling ionospheric disturbances in the nighttime. So this is not our focus. Our focus is in the daytime MSTIDs. So the objective of the present study is to compare the longitudinal seasonal variation of the daytime MSTID between GAIA and GPS observation. And also we want to understand what is the underlying physical mechanism which causes the MSTIDs in the GAIA model that we want to study here. In order to do that, we use the GPS observation from several parts of the world. From this GPS TEC data, we have obtained the MSTD perturbation. How we obtained the MSTD perturbation? Just we took we removed the 1 hour running average TEC from the actual TEC for each satellite and receiver pair. From that we can get the slant TEC value perturbation. Then we converted that slant TEC into the vertical TEC. And how the MSTIDs are defined? The MSTID is defined with the ratio between the standard deviation of the 1 hour TEC divided by the 1 hour mean TEC. So on the other hand, GAIA, which is the so many things were already explained by Dr. Miyoshi already in the first talk. So just once again I will remind you. It is a coupled model of the lower atmosphere and the ionosphere and the ionospheric electrodynamics. So it is a coupling of three models. In the upper atmosphere, it is having the high resolution, high horizontal resolution of 1 degree latitude and 1 degree longitude. And the vertical resolution is 10 kilometers. The temporal resolution is 10 minutes, which is the high resolution GAIA is used in this study. In order to determine the MSTD activity, we have followed the same method what we used in the GPS. The only difference is here we have used the 2-hour running average of TEC. That 2-hour running average TEC is separated from the actual TEC to get the perturbation. And in order to define the MSTID, we have defined it, the ratio between the standard 2-hour standard deviation of the TEC perturbation divided by the 2-hour average absolute TEC value. So how the daytime MSTIDs looks in the observation and the model simulation. I think you can able to see my cursor. Yeah, this is the observation, the right side figure. You can see red and blue patches which represent the daytime MSTID. The phase fronts are aligned in the east-west direction, and the left side panel shows the GAIA simulated daytime MSTIDs. You can see the GAIA can able to simulate the daytime MSTID activity. So globally, how the wave perturbation in the TEC data. You can see there are so many waves in different direction, and in order to see the daytime MSTID propagation direction, just we made the north-south geogram. Here you can see the phase front from the pole to equator progression. So which means they are propagating towards equator. So in order to study the longitudinal variation, we have taken 4 places in the northern hemisphere as well as 4 locations in the southern hemisphere. For example, in the northern hemisphere, we used the western USA. These dots are mentioning the GPS receiver location, and eastern USA, Europe, Japan. In the southern hemisphere, we use South America, South Africa, Australia, and New Zealand. So as I told in my introduction, one of the main causative mechanism for the daytime MSTID is the gravity waves. How we will get the gravity parameters or gravity presence? One of the best parameters is the wind variance. So we derived the zonal and modal wind variance using the GAIA winds, zonal and modal winds for the year 2011. This study is carried out for the year 2011. So here the U prime whole square mentioned denote the average zonal wind variance. U is the zonal wind, U bar is the 2-hour average zonal wind. So this using this equation, following this equation, we derived the wind variance, and similarly modal wind variance also derived. And the mean wind variance is the sum of zonal and the modal wind variances. So in this study, mostly the zonal wind variance is used for the comparison. So this is the seasonal and temporal variation of daytime MSTID activity. The first top panel shows the observation from the GAIA, observation from the GPS, and the middle panel shows the GAIA simulated MSTID activity, and the bottom panel is the standard deviation of modal wind variance from the GAIA simulation. And please note that here you can see around the sunrise and the sunset time, there is enhancement in the TEC MSTID activity. It is not actual MSTID activity. This is due to the sudden drop of density variation in the ionosphere due to sunset and sunrise. So only the statistics will be considered only apart from the sunrise and sunset time. If you are seeing the local time variation, you can see around before noon and after noon, the MSTID activities are more, and it is more during the winter month in the observation, and this feature also can be seen in the GAIA simulation. But when we are seeing the modal wind variation, it is showing the 2 peaks. One is during winter, another is during summer. So in order to see the clear seasonal variation, just to be average the daytime MSTID activity and the wind variance from 19 LT to 15 LT. In these figures, the right side panel shows the standard deviation of wind variation, and the left side panel left side axis indicates the MSTID activity. You can see the observed MSTID activity, which is red color, and the model simulated MSTID activity, which is in the black color, are going 1-to-1. So they are matching well in the almost all the location except European sector. There is some discrepancy. And when we are considering the zonal and modal wind variation, it is showing the 2 peaks. peaks. One is during winter, another is during summer. So the overall, the winter peak is matching with the MSTD activity peak, which means the winter time maximum of MSTD activity is caused by the gravity amplitude. So this is the seasonal and temporal variation of MSTD activity in the southern hemisphere. You can see the top panel from the observation and the middle panel from the GAIA simulation MSTD activity, and the bottom panel is the middle wind variation, similar to the northern hemisphere. So the one thing here is that here also you can see, as far as the local time temporal variation concerned, the maximum occurrence is happening afternoon or before noon. So it is less during the midday. So, and the maximum occurrence is observed during the southern hemispheric winter time. So, in order to see the seasonal variation, we have done the daytime average from 9 to 15 LT. You can see very clear seasonal variation of maximum around the southern hemispheric winter in all these 4 locations. And what about the wind? If we are seeing the wind similar to the northern hemisphere, in the southern hemisphere also, wind is showing the 2 peaks. One is in the winter and another is in the summer, except the New Zealand. New Zealand shows only 1 peak, which is around the southern hemisphere winter time. And more interestingly, if you are looking at the South African sector, the wind amplitude during summer is higher than the wind amplitude during winter. However, the MSTD activity is more during winter than summer. So there is a clear discrepancy. What could be the possible reason? That will be discussed in the later slides. Before that, I want to discuss the longitudinal variation. So in order to see the longitudinal variation of MSTD activity, we have picked up the peak of the MSTD activity in the each location. The left panel is for northern hemisphere and right panel is for the southern hemisphere, and the x-axis show the different location and the longitudes. So if you are seeing the northern hemisphere, there is very clear longitudinal variation with the maximum MSTD activity is noticed in the Japanese sector, and the minimum is noticed over the Western American sector, which is showing the very good consistency with the earlier report by Kotake et al. 2007. And in the southern hemisphere, the MSTD activity is more over the Pacific Ocean region, which means the New Zealand sector and the South American sector, and it is very less over the African sector. But at the same time, there is some small discrepancy between the observation and the model over the African sector. Okay. In overall, the GAIA model can successfully reproduce the longitudinal variation of the daytime MSTD activity. So since it can produce the longitudinal variation, then what could be a source for the longitudinal variation? In order to do the check that, we have checked the wind variance, which is the representative of gravity activity. You see that with it is, this is the red color is the MSTD activity from the GAIA simulation, and the blue dots mentioned the MSTD gravity activity or the wind variance from the GAIA model simulation. You see, this is the left panel is for the northern hemisphere and the right panel for the southern hemisphere, and they are showing 1-to-1 correlation, except some places there is some small discrepancies. So which means the longitudinal variation in the GAIA model is caused by the gravity activity. Then, as I explained in my previous slide, there is a clear discrepancy in the wind amplitude and the MSTD activity occurrence over South Africa. In order to understand that, we have carried out further study. We took a typical day during summer when the MSTD activity is noticed during notice. You can see this is the altitude in the left side panel. Just see the top one. This is the altitude latitude cross section of wind perturbation. You can see very clear gravity phase front, which is starting from the pole side up and the equator side down, which means the wave is propagating towards pole, and the phase front is almost perpendicular to the black line is the magnetic field line. The phase front is almost perpendicular to the magnetic field line. As you know, when the gravity waves are propagating, the neutral atmospheric particles or the gas molecules will oscillate along the phase front of the gravity waves. Please note that. And this down one shows the electron density perturbation, simultaneous electron density perturbation. This is the perturbation amplitude you can see here. In order to see the amplitude variation clearly, just we have done the latitudinal average. It is the height variation of the middle wind variation. You can see the middle wind variation exceeds more than 25 meters per second. However, the electron density perturbation is only 15%. And this is during summer over South Africa. And another typical day we took during winter over South Africa. And here you can see this is same the altitude latitude cross section of the middle wind variation, and the bottom one is the electron density perturbation. The phase front is aligned from the low latitude equator to the bottom polar region, so which means the wave is propagating towards equator. So the phase front is almost parallel to the magnetic field lines. As you know, this particle will oscillate along the magnetic field line. Then if you are seeing the middle wind amplitude, the amplitude is only 15 meters per second, and the electron density variation is around 20%, which means even though in the summer time the amplitude of the wave perturbation is more, but the electron density variation is less because of the propagation direction. And as you know, when the electron density, when the air, as you know, in the in the ionosphere, ions are magnetized, so it is difficult to move the ions across the magnetic field. That's what happening during the winter. Even though the amplitude is more, but the air molecules are oscillating perpendicular to the magnetic field, so the electron density amplitude perturbation is very less. But in the winter time, though the amplitude is less, but the molecules are oscillating along the magnetic field, so it can easily move the electron density. So which would be the reason, though the amplitude is less, but we could able to see the more MSTID activity during winter time. So in a summary, the winter peak amplitude of the middle wind variation coincide with the winter peak of the daytime MSTID most of the location. This is because of the large amplitude is responsible for the winter time MSTID activities. And in the GAIA simulation, the propagation direction of gravity waves are equatorward during winter and poleward during summer. So when the waves are propagating towards equator, the ion perturbation velocities are large, and for the poleward it is less. So therefore, the propagation, in addition to the amplitude of the gravity, propagation direction of the gravity also responsible for the largest MSTID activity noted over South Africa. As a conclusion, the GAIA model can successfully reproduce the seasonal variation and longitudinal variation of the daytime MSTID activity, and the propagation direction of gravity wave causes the seasonal variation. And the global distribution of the gravity wave activities in the middle atmosphere and lower atmosphere may be the responsible for person for the longitudinal variation of the daytime MSTID activity. Thank you very much for the.
Thank you, Sivakandan. Thank you for this nice talk. We are a little bit running out of time, but I think we can, if someone has a question, a quick question. Otherwise, we are going to move to the next speaker. And
Fabio, I have a quick question.
Igor.
Sivakandan,
yeah.
May you, what kind of source of the gravity waves is producing this longitudinal variation? Because I saw in South Hemisphere there are more gravity wave activity in South America. Do you believe that it is associated with the convection or mountains or something like that?
Yeah. Actually, what I want to mention, I was in the rush, I forgot to mention here. What we believe that if you are seeing the phase front, most of the phase fronts are ending around 120 kilometers or above 110 kilometers. So which means that whatever we are seeing in the thermosphere, which may be the secondary waves rather than the primary waves. And one thing, as far as the thermospheric gravity activity concerned, as you know very well, in the Brazilian sector, there are two dominant. It is one of the potential gravity wave source region where the convection also there, as well as the mountain region. So both can have the sufficient. I mean, both can have the important role. Especially as far as the secondary waves concerned, the mountain waves may have more role than the convection probably.
Okay, thank you. Just to remind on all of you, you can ask questions through the Q&A. So after the speaker can give your an answer. So let's move to the next speaker. Is the last talk of this session. Professor Manilo Marques from Universidade Federal do Rio Grande do Norte. Manilo, thank you for coming, and thank you for this presentation.
Thank you, Fabio. Can you read me well?
Yes, yes.
Okay, thank you. I just wait to close the presentation because I cannot. I can't to show my screen. Okay, thank you.
Okay.
I will. Okay. Can you see my screen?
Yes, now we can see it.
And now?
Yes, now we.
It's in full in the presentation mode.
Yes, it's in the presentation mode.
Okay, thank you. Okay, I will talk a little bit about the open source develop of TEC-MAP. Okay, using not a very used interpolation technique to the equatorial region, but we will try to do that. Why? This is just a summarize of the presentation, but why we use why we develop open source TEC-MAP. During my class in the master engineer, space engineer course, I realized that it's not so easy to have access to the TEC-MAP program. And of course, it's not easy. If you have access, it's not easy to modify them. Why you want to modify and you have access to modify them? Because we want to study the interference of the plasma, space plasma, ionospheric plasma, and experiment and satellites and something like that. So I realized that not easy to find that. So we decided to develop one. It's open because everyone can take. It's will be distributed by GitHub, and of course, if you have the code, it's use Python. It's very easy to modify them. Okay. Why we decide to use the Kriging interpolation? The Kriging is a linear interpolation method, and use the sample value. In our case, it's VTEC. It's a vertical total length content in the ionospheric piece point, and the variogram that come from this data. Okay, to estimate the VTEC in the different region that we cannot have GNSS station. Okay, So what is the Kriging technique? It's the Kriging technique use the weight to estimate in our case is VTEC, okay, and this weight is depend of the distance of this point to the others VTEC that you have. So this is just one example. We have the VTEC, the observation VTEC that you come from the satellite and then station, and we want to estimate the VTEC in the different point that we have not station. So this is the Kriging use the weight, this function rate that comes from the points that the VTEC that you can observe, and this weight depend of the distance from this point. Okay, so in this case, the big problem to use this technique is because the weight function, but the weight function it comes from the variance. The variance between the variance and between the VTEC, the observation VTEC. In this case, the h it's distance. So, and of course, this is the other problem. To use the Kriging, we need to assume that the VTEC, they observe the VTEC, it's locally stationary. This is not true almost the time. Of course, we use, for this case, we use the very basic Kriging. It's the ordinary Kriging that can assume that the weight have this condition that you are shown. So when you use the minimize this function, we can have this equation that you can modify then using the matrix format, and you use the method, for example, the Gauss method to solve this equation, and you can take this weight for the use the Kriging interpolation technique. And this is a very good. This method is very good because it's a very fast. It can run in the computer, in the personal computer, that you just can put them to run, and 1 or 2 hours it's complete one day of the TEC. So, but of course we needed to adapt all the methodology to use this Kriging. For our case, we in the program that we are developing, we select the period. The program now is configured to all South America, but we are show here only Brazil. But we select the period that you can create the map. This program go to the database, IGS, Unavico, RBMC, and there are others that are implemented, but it's the basic, this database is more important, and go to the database. And of course, here we are interested only in develop the map. So we not spend the time to develop the program to generate the VTEC, the vertical total electric content. Because that we use the GOPSIMALA GPS TEC program. Okay, when the program run the GOPSIMALA, we start a pre-processing to remove the bad bad data, the outline point, and to rearrange data set. In our case, the minimal temporal resolution is 2 minutes. We have tried less than, but because the noise in the very noise in the data, it's become a little difficult to generate the map with the good accuracy. And also we pre-processing in selected data only with the elevation, with the specific elevation. Here I put to 30, but you can select less until less elevation. It means that you have more data. We when we finish the pre-processing, we generate the ionospheric grid point that in this version use the uniform grid 1 by 1 degree, but because the non-uniform distribution of the station, we have less in some region of the for example, I will show here in Brazil, you can have less one high resolution in some region, we want less resolution in other region. But here I put the uniform grid. The next step in the new version, I will put the non-uniform grid. Okay, and we started to run the Kriging interpolation algorithm, and the Kriging use the Kriging run and use some ionospheric data from our the first we select some data in our database and remove this data, and we run the Kriging interpolation, create the map, and we compare this new map, the map and this data that you can remove, and we test, we make the mean square error and try to be the error will be the minimal. In the quiet day, we have less than one, in the plasma bubble event, for example, we have the minimal is 3, but we try to improve the algorithm. Okay, we run this for all ionospheric piece points, and we generate them, we save and generate the move. Of course, it's all these processes automatically. We just select the period and put it to program to run, and in the end, we'll take the data and the movie. So I will show the 3 case study. It's a calm day. This calm day, we select the day with the planetary index less than 4, the plasma bubble event, and the magnetic storm event. Okay, this is the calm day. I will show here. This is a very difficult you see, because there are many. We use the 5 minutes resolutions, so this is difficult. I put to all the image, but this is just one select image that we come from the data. It's for in the time, in the universal time. Okay, and if possible, I will run the move, but I need the feedback if you see my screen.
Not yet.
We can see the screen, but
There is a black.
Okay.
There's a black. Now I think we can't see nothing. Just the black screen.
Okay, let's try to and now?
Now we can see.
Okay, let's try to. Okay.
Is this a movie?
Yes.
It's not running.
Okay.
We can see the image, but just a static image.
Let's try to run the.
Now it's running.
This is the map generated by the program. This is a quiet day. Okay. Okay, now return and we try to see the plasma bubble that we can generate. This is the plasma bubble. This is just some frame of the event that we start in the midnight and universal time, and you try to see the evolution of the plasma bubble that in the screen. Okay, let's do the same to plasma bubble. When you start to see my screen, my movie, please send. We start to see my movie.
Yes.
This is the formation of the plasma bubble that you can see. It's almost clear. And for in the last case, we show the magnetic storm that we identify by the symmetric H index that are shown in the image, and this is the some frame from the program. I just created the movie for one part of the storm that I will show here. When you see my screen, you see the movie.
We can see the screen, but the movie is not running.
Okay, this is the
now it's
here is the case of the magnetic storm that are run. There are a very interesting event here that we are happy to show that the map is very accurate, that you can see here in the screen generate the plasma bubble by the very fast increase in the density that you can see here in the generate the plasma bubble, because the very screen that happened in the map that I just show one part here. You can see the increase in the density, in the plasma density, and generate the plasma bubble, but it's a very fast, and I use the I use the low resolution in time because it's 3 days of moving. And this is the magnetic storm. There are all the event that we see in the plasma, and the next step, we will compare the result with the other result that come from the other program. We create the non-uniform grid to increase the resolution when you have we have the density of the station, the GNSS station, and we want develop a friendly front end, because it's become easy to everyone use, and of course, if you just want to use, don't want to modify the program, it's just use. We want a very friendly front end that's easy to see, and this is all. I finish here. This is in the develop program. I hope that the next year will be available to everyone that want to use. Okay. If I have questions, comments.
Thank you, Manilo, for a nice talk. It's good to hear that you are developing a new technique. We have time for a quick question, if someone has. Igor?
Yes, Manilo, what's the temporal and the best temporal and spatial resolution of your TEC-MAP?
Okay, it's 2 minutes. I have tried less, but because the very noise data, we cannot. Of course, we can smooth the data. We can use some technique to remove the high frequency oscillation in the VTEC. You can increase the temporal resolution, but if you remove, you cannot see what's happening. but the minimal the high resolution, the temporal resolution it's 2 minutes, and it's spatial it's 1 degree, but 1 degree because I use the uniform grid, because there are some region in Brazil that has very low density of station, but in the high density region that you can have many stations, you can go to the 0.5 degree the spatial resolution. Okay.
Okay. Thank you.
Of course. This program will not be only the TEC-MAP. Okay, this program, the main goal of this program is to have the tools that you can analyze the atmospheric event and ionospheric event. It's together. We are also developed the program that you can couple to the atmospheric event that's coming from the reanalysis data. We already have some case that we analyze. It's Katrina storm. We put Katrina storm behind the ionospheric map. You see and you track the storm, the atmospheric storm. We track and we see the formation of the. Of course, it's not a very high resolution yet, but you can see the formation of the travel ionospheric disturbance following the storm. But in this case, for Katrina, it's a very big storm in that you see in the South America.
Okay, thank you, Manilo. There is one question from Rodolfo. He's asking if this TEC-MAP program is available for download for all of users.
Not yet, but he can send me an mail. I put my contact there, and of course I will send the algorithm.
Okay, thank you. So now we can finish the session, this first part of the section. I'd like to thank all of the speakers and also all of the audience from this Zoom room and also from YouTube. Igor, if you have some announcement.
Okay, Fabio, thank you for this session. Let's have a break of 5 minutes to drink a water or something like that. And we will start the next session at 11 and 10. It's okay? Hi, everybody.
Oi, Igor. Tudo bem?
Tudo bem. Vamos aqui dar início à sessão 2. Eu vou fazer uma breve chamada e passar a palavra para você. Então.
Tá bom. Beleza.
Acho que só falta o professor Takahashi entrar na sala, os demais já estão na sala.
Tá bom, tudo bem.
Let's start the second morning session. The chair of this section is Professor Fernando Bertoni from UEPB. Professor Fernando, please.
Good morning, everybody. I introduce you to the session about the upper atmosphere. And the first talker will give us a presentation about planetary wave effects on the ionosphere. He is Dr. Yosuke Yamazaki from University of Potsdam, from the upper atmosphere and ionosphere in Germany. So, Professor, you have 20 minutes and 3 minutes for questions. Please, go ahead.
Okay, thank you for the introduction. I'm trying to share my screen now.
All right, we are able to see your PowerPoint.
Okay, very good. Yep, and do you also see my cursor moving?
Please?
Do you also see my cursor moving?
No.
Yes, I can.
Moving?
Okay. So this guy, yeah. Okay, hello everyone. My name is Yosuke Yamazaki. I'm a researcher at the GFZ Potsdam, Germany. In this presentation, I'm going to talk about planetary wave effects on the ionosphere. Okay, so our primary interest is to get a better understanding of the day-to-day variability of the ionosphere or the ionospheric weather. The state of the ionosphere changes significantly from one day to the next, and it's very difficult to predict its behavior. There are 3 sources that are important for ionospheric variability. First, solar energetic radiation, such as extreme ultraviolet and X-ray, can directly affect the ionosphere. Second, ionospheric variability can arise from solar wind magnetosphere ionosphere coupling, which is most evident during geomagnetic storms and substorms. Finally, the ionospheric variability can also arise from atmospheric waves that are coming from the lower atmosphere and middle atmosphere. And this presentation is going to focus on the third process, and we are going to look at the response of the ionosphere to the wave forcing from below. Okay. So this is an illustration of vertical coupling by atmospheric waves. So the Earth's atmosphere can support various types of waves, such as gravity waves, tides, and planetary waves. These waves are primarily generated in the lower atmosphere, but some of them can propagate vertically upward into the middle atmosphere and the upper atmosphere before getting dissipated. And there are several ways by which atmospheric waves can affect the ionosphere, but the primary mechanism is the E-region dynamo. So there is a systematic difference between the way atmospheric waves affect ions and electrons in the E-region ionosphere. As a consequence, electric fields and currents are generated in the ionosphere, and these electric fields are mapped into the F region along the equipotential magnetic field lines and redistribute F region plasmas, which are moving mainly by E cross B drift. So this way, the atmospheric waves reaching the E region ionosphere can affect the entire ionosphere. Okay. The Southern Stratospheric Warming, or SSW, in January 2009 was a very good example of vertical coupling by atmospheric waves. So the left panel here shows changes in polar temperature and the zonal wind in the stratosphere, indicating the occurrence of the SSW here. The panel 3 shows the ground magnetic field variations associated with the equatorial electrojet, which is E-region currents at the magnetic equator. The x-axis here is the date, and y-axis is the local time. And the vertical dashed line corresponds to the day of maximum temperature perturbation in the stratosphere. And the color indicates the strength of the equatorial electrojet. The red is eastward currents and blue is westward currents. So before SSW, the equatorial electrojet during daytime was mainly eastward, which is normal. But after the peak SSW, the pattern of the daily variation is very different, and it's now eastward in the morning and westward in the afternoon. So there is a semi-diurnal perturbations in the equatorial electrojet. The panel 4 shows total electron content, TEC, in the American sector. This is a few days after the peak SSW. And here it shows deviation of TEC from a quiet time reference as a function of local time versus latitude. Similar to equatorial electrojet response, TEC perturbations are enhanced during the morning and reduced during the afternoon. And many scientists suspected that these semi-diurnal perturbations observed during the SSW may be due to the semi-diurnal tide. And in fact, modeling studies found that there was an enhancement in semi-diurnal tides in the middle and mesosphere and lower thermosphere during this SSW. So these figures show the figure 5 and 6 shows the amplitude of the semi-diurnal tide in zonal wind at the height of 110 kilometers. And panel 5 is solar semi-diurnal tide, and panel 6 is lunar semi-diurnal tide. As we can see, both ties are enhanced following the SSW. And that can explain the semidiurnal perturbations observed in the ionosphere during this SSW event. So this was just one example, but atmospheric tides are in general recognized as an important source of ionospheric variability. Our question is very simple. What about traveling planetary waves, which are not nearly as much studied as atmospheric tides? Our study is also motivated by recent global satellite measurements of ionospheric parameters that often show multi-day oscillations. Here I'm presenting examples where the equatorial electrojet intensity show multi-day oscillations. In different panels correspond to different event. And in all cases, you can see the equatorial electrojet intensity is going up, down, and showing some oscillating behavior. Okay, let me briefly describe what traveling planetary waves are. So in the broad sense, planetary waves are global scale oscillations of atmospheric parameters. They can be either stationary or traveling in the zonal direction. What we are particularly interested is Rossby normal modes, which are free oscillation of the atmosphere as predicted by classical wave theory. They have discrete zonal wave number, 1, 2, 3, and so on. And each mode has a certain oscillation period. The most famous ones are those with zonal wave number 1 and period at 5 days, 10 days, and 16 days. Rossby normal modes are all westward propagating, and each mode has a certain latitude versus height structures. Latitude structure is given by a half function, and vertical structure is that of a Lamb wave. These figures show the latitudinal structures of 5-day mode, 10-day mode, and 16-day mode, and predicted by classical wave theory. And Z is geopotential height, U is zonal wind, and V is meridional wind. And we can see here that the latitudinal pattern of these modes are different for different modes. Classical wave theory assumes very simplified atmosphere without dissipation or zonal mean winds. So what we observe in the real atmosphere are slightly different from classical Rossby normal modes, and they may be called quasi-normal modes. The upper panel here shows the number of westward propagating planetary waves with zonal wave number 1 as detected in stable temperature measurements in the middle atmosphere. As we can see here, the occurrence of wave activity is concentrated around the period of 6 days, 10 days, and 16 days. So they are called quasi-6-day wave, quasi-10-day wave, and quasi-16-day wave. And the bottom panel shows the latitude versus height structures of these waves, also derived from stable temperature measurements. Now going back to the multi-day oscillation of the equatorial electrojet, which I showed earlier, these oscillations have period about 6 days in all cases. So our immediate speculation was they may be somewhat related to the quasi-6-day wave in the middle atmosphere. So we look at the spectrum of the equatorial electrojet oscillations. Since the satellite collects the data from all longitudes, it is possible to determine the zonal wave number of oscillation as well as period of oscillation. So these panels shows zonal wave number versus period spectrum of the equatorial electrojet intensity during the event which I showed in the previous slide. So corresponding to these events. Interestingly, in all cases, the dominant spectrum corresponds to the westward propagating oscillation with zonal wave number 1 and period 6 days. I forgot to mention, but the positive zonal wave number correspond to westward propagation and negative zonal wave number correspond to eastward propagating waves. So the results support the connection with the quasi 6-day wave, which is also westward propagating with zonal wave number 1. We also analyze the geopotential height data from ORA-MLS, which is another satellite taking data from the middle atmosphere. And the results confirm the presence of the quasi 6-day wave during these events. So in all cases, the peak spectrum corresponds to the westward propagating 6-day wave with zonal wave number 1. So the observed 6-day oscillations in the equatorial electrojet intensity can be reasonably associated with the quasi 6-day wave in the middle atmosphere. So we showed that when there is a 6-day oscillations in the equatorial electrojet, we can find the quasi 6-day wave in the middle atmosphere. But we don't know if the other way around is the case. So we now consider whether there is one-to-one correspondence between the quasi 6-day wave in the middle atmosphere and the 6-day oscillations in the ionosphere. To this end, we use total electron content maps provided by IGS. IGS produces the global TEC maps every 2 hours using ground-based GPS measurements. We use 18-day time window, and Fourier analysis is performed to extract westward propagating 6-day oscillations with zonal wave number 1. The analysis is performed separately at each local time and magnetic latitude. Panel 1 here shows the all-time average of the amplitude of the 6-day oscillations in TEC. We can see large amplitudes on both sides of the magnetic equator during the afternoon local time. The results strongly reflect the structure of equatorial ionization anomaly. And the results suggest that these 6-day TEC oscillations are probably produced by the modulation of equatorial plasma fountain. Panel 2 shows the relative amplitude. This is the amplitude divided by zonal mean TEC. In this climatological average results, the maximum amplitude is about 5% of the background TEC. Now we are going to look at the 6-day oscillation amplitude in TEC for different years. The left panel is for the solar minimum years of 2008 and 2009. And the right panel is for solar maximum years of 2014 and 2015. As you may notice, the amplitude is much larger during solar maximum. Interestingly, this solar activity dependence virtually disappears when we look at the relative amplitude rather than the absolute amplitude. And in this case, the amplitude of the 6-day oscillation is comparable between solar minimum and solar maximum. And the annual maximum amplitude is about 10% of the zonal mean TEC. So repeating my point again, so in absolute amplitude, they are solar activity dependent, but in the relative amplitude, they are not strongly so. Here we compare the amplitude, the relative amplitude of 6-day oscillations in TEC versus the amplitude of the quasi 6-day wave in geopotential height in the middle atmosphere. The red line shows the 6-day oscillation amplitude in TEC, and the blue line is the quasi 6-day wave in the middle atmosphere. And there is a very good agreement between the two. The results indicates that whenever there is a strong quasi 6-day wave in the middle atmosphere, there is a large 6-day oscillations in TEC. So this is from 2006 to 2011, when solar activity was relatively low. And this is from 2012 to 2017, when the solar activity was relatively high. So there is a nearly one-to-one correspondence between the two, regardless of solar activity. Finally, to add more recent exciting topic to this context, I would like to mention the extraordinary SSW of September 2019. This SSW took place in the southern hemisphere, in contrast to more frequent northern hemisphere SSW. As it turned out, this Antarctic SSW is an excellent example of whole atmosphere coupling by traveling planetary waves. Here I'm showing 5 figures presenting data from different height regions. Panel 1 and 2 depict unusual temperature and wind variability in the stratosphere associated with this SSW. The red line shows the data from 2019, and gray lines are data for other individual years between 1980 and 2018. Black dashed line is a climatological average. So both temperature and wind variability in 2019 were very different from the climatological behavior. Panel 3 shows enhanced activity of westward propagating planetary waves with zonal wave number 1 observed following the SSW. So there is enhanced wave activity with periods around 4 days and 12 days, and waves activity is most strong around the period 6 days. At this time, Swarm satellite detected quite strong 6-day oscillations in ionospheric parameters, which are presented in panel 4 and 5. Panel 4 is for equatorial electric field, E region parameter. Panel 5, topside electron density, F region parameter. In both cases, we can see 6-day oscillations. Since this 6-day oscillation has zonal wave number 1, the variations are out of phase for the longitudinal separation of 180 degrees. So this is very interesting event. So if you have relevant data, I would strongly encourage to look into this SSW event. The results may provide some interesting insight into the vertical atmospheric coupling by these traveling planetary waves. Here's a summary and conclusions. So we show that equatorial electrojet intensity occasionally shows 6-day oscillations, and these oscillations are westward propagating with zonal wave number 1. They are accompanied by quasi 6-day wave in the middle atmosphere. Similar oscillations are also found in total electron content at low latitudes, And there is nearly 1-to-1 correspondence between the quasi-6-day wave activity in the middle atmosphere and 6-day oscillation amplitude in TEC. Finally, September 2019 Antarctic SSW event provides a great opportunity to investigate vertical coupling by traveling planetary waves. That's all about, and the results I showed in this presentation are mainly documented in our recent publications. So for more details, please check out our papers. Otherwise, yeah, that's it. I would be happy if there is. I would be happy to answer the questions if there are some.
Thank you very much, Dr. Yosuke. Dobo arigato. Well, you have question, people, participants, panelists.
Are you still seeing my presentation screen, or what are you?
Yes.
Do you see now?
Yes, we can see your screen.
Oh, okay. So I will keep it this way.
I have a question. First,
Who is talking, please?
Fabio.
Fabio. All right.
Thank you, Dr. Yamazaki, for this nice talk. My question is about the interaction, the possible interaction between planetary waves and the diurnal tides. My question is if you have observed signs of the planetary wave tide interaction in this ionospheric data.
We looked at that for this SSW event. So we looked at the ionospheric data. We used the global GPS, global TEC maps, and we checked if we see the evidence of the secondary waves due to the nonlinear interaction of quasi-6-day wave and tides. And the evidence suggests that there was a wave effect from the quasi-6-day wave semidiurnal tide interaction. So short answer to your question is yes.
Thank you.
But probably I imagine the contribution of secondary wave could be the case by case. I'm not sure if the September 2019 SSW case will represent the ionospheric effects during other quasi-6-day wave events. So I think it's important to look at the individual events carefully.
All right. Thank you once more, Dr. Yamazaki. And let's go. Anyone else wants to make a question or a comment? So we go further to the next presentation, right? Thank you very much, Dr. Yamazaki. The next talk is entitled Nonlinear Interaction between the diurnal tide and an ultra-fast Kelvin and its effects on the equatorial mesosphere, thermosphere, ionosphere system by Fábio Egito from Federal University of Campina Grande, or Universidade Federal de Campina Grande, Brazil, from the Department of Physics. Dr. Egito, please, go ahead.
Thank you, Bertone. I'm going to share my screen. Can you see it?
Yes. It's very good, very nice. Okay.
Okay, now it's in the presentation mode. Okay. Thank you for the introduction. This talk is basically summarize results that we recently published, and the first publication is about the presence of ultrafast Kelvin wave in the air globe, and the second one address the variability of the equatorial ionosphere due to secondary waves. This is the outline of the talk. First, we investigate the presence of ultrafast Kelvin wave in the MLT air globe. And to do that, we use air globe data from Cariri observatory, measured by a photometer. The photometer measures 3 emissions and also the OH temperature. The photometer measures OH, O2, and the green line emissions coming from MLT region. So here's it's a special case I would like to show. These right panels shows the intensity of the emissions. In the top, we have the green line intensity. Here, we have the O2, OH, and at the bottom, we have the OH temperature. We looked for periodic variations associated with ultrafast Kelvin wave. These periodic variations associated with Kelvin waves, with ultrafast Kelvin waves, have periods between 3 and 4 days. And to do that, we analyzed a sequence of nights. Each group of data here corresponds to one night of air globe observations, and we put all together and perform a spectral analysis with the Lomskargo periodogram. And the periodogram are shown here at the left panels. What we can see is that for O2 emission, OH emission, and the OH temperature, there is a clear peak around 3.5 day in the periodogram, which corresponds to the signature of the ultrafast Kelvin wave. However, when we look at the green line spectrum, we can't see this same 3.5 day oscillation. And we started asking ourselves why we didn't see this 3.5 day peak in the OH, in the green line emission. Once we ask that, we also think about possible response, and one of them is this might be related to the influence of the atmospheric tides. So we look more carefully the effect of atmospheric tides. Here in this figure, we have the individual nights of the green line intensity during that time. That's in March 2005. There are 10 consecutive nights of air glow measurements. And what we can see here is that the green line intensity usually is high in the beginning of the night, and as the night goes, the intensity decreases. And this is a very well-known feature of the effect of the diurnal tide in the air glow. However, we can see that in a few days, for example, here in day 8, this is March 8, and in the 11, that the intensity of the emission in the beginning of the night decreases, and we start to investigate more deeply these possible effects of the diurnal tide, because in the equatorial region, air glow is strongly driven by the diurnal tide, especially before midnight. That's what we are seeing here. So we performed a new analysis, and now we just analyze the post-midnight data. Here, these plots show in the right the intensity of the tree emission and the OH temperature, but in this case, only with post-midnight data. And then we performed a Lom's-Cargo spectral analysis. And now, when we consider only post-midnight data, we can see that the 3.5-day signature of the ultra-fast Kelvin wave is very well defined in all of the emissions and also in the temperature. So what we can conclude that is that the variability of the diurnal tide in a short time period may affect the air glow, and also affect the variability associated with the ultra-fast Kelvin wave. And one possible explanation to this short time tide of variability is the non-linear interaction between planetary scale waves and atmospheric tides. Just a quick review. The linear wave theory that solves the governing equations only keeps the first order terms, and this explain most of the tides, planetary waves, and gravity waves we observe in the atmosphere. However, there are some signals that cannot be explained only through the linear wave theory. For example, the modulation of the amplitude of the atmospheric tides at the period of planetary wave, as is this case I show here in this figure. Here we have the modulation of the diurnal tide amplitudes by the 16-day planetary wave observed in the MLT neutral wind. And there is a theoretical development for the non-linear theory, and following Teitebal and Vial, they kept second order terms in the governing equations and looked for possible solution. And what they found was that when the non-linear interaction takes place, and they keep these second order terms in the equation, there are the generation of secondary waves. Secondary waves that are generated by the interaction between the primary waves. In this case, the primary waves are the atmospheric tides and the planetary scale waves. And these secondary waves generated through nonlinear interaction have frequencies and wave numbers, zonal and vertical, that are the sum and the difference between the frequencies of the primary waves. So when the nonlinear interaction takes place, from the theoretical point of view, there are the generation of two secondary waves. Then at Cariri, besides the air globe measurements, there are also a meteor radar that provide us zonal and meridional winds between 80 and 100 kilometers. Then we analyzed the zonal wind during the same time we observed the ultra-fast Kelvin wave in the air globe. Here we have in the top panels the zonal and the meridional wind at 91 kilometers. And in the bottom panels, we have the Fourier power spectrum. We are looking for the possible periodical oscillation present in this data. And what we can see is that in the zonal wind, we have here the signature of the diurnal tide with one cycle per day, and also the signature of the ultra-fast Kelvin wave. But in addition to these two waves, we have also a peak here in the spectrum at the frequency of 0.75 cycle per day. And this figure and this peak correspond to one of the
sorry, just to remind you, we have just 3 minutes more.
Okay. I'll try to speed up. Okay, so
with no questions.
Okay. So we have this peak associated with this secondary wave, which is exactly the difference between the frequency of the diurnal tide and the ultra-fast Kelvin wave. And when we think in period, this secondary wave has a 1.3 day period. So we also analyze the amplitude of the diurnal tide, and this plot shows it. And we can see there is a periodic modulation of the amplitude with period of about 4 days, which is confirmed by the wavelet spectrum. Here at 82, that we can see this modulation, and we can see the modulation at 91 and 98 kilometers. So once this secondary waves is generated, it can propagate independently, and then we check what happened with this wave. And what we saw was that this secondary wave present a upward propagation with a vertical wavelength about 45 kilometers, and with this characteristics, this wave. This secondary wave could penetrate in the region dynamo, and there are modeling studies that support the penetration of secondary waves in the ionosphere. So we also looked for the sign of this secondary wave in the ionosphere. We analyzed virtual height and critical frequency measured by a ionosonde at Fortaleza, and in this data we could also observe the signature of this 1.3 day wave in this ionospheric data, and this suggests that this 1.3 secondary wave may have penetrated into the region dynamo, and through the modulation of the wind system in the E region dynamo could affect the variability of the F region through the vertical drift. And also this, as I said before, there are modeling studies that support this kind of coupling mechanism involving secondary waves. So this is the summarize of this talk. Thank you.
Thank you, Fabio. Any question, at least 1 minute? Any question?
Can I ask a question?
Yes, please. Go ahead.
Is the vertical wavelength of 1.3 day wave consistent with the vertical wavelengths predicted from the nonlinear interaction of tides and ultrafast Kelvin wave?
I tried to do this calculation, but I couldn't find a good agreement between this observed vertical wavelength and the prediction of the theory. I mean, they don't agree.
Okay, interesting. Thank you for answering.
Thank you, Fabio. The next talk is entitled as Equatorial Plasma Bubble Observations, Past and Present, by Dr. Hisao Takahashi from National Institute for Space Research, São José dos Campos, Brazil. Professor, you have 12 minutes plus 3 minutes for questions, okay? Thank you.
Fernando.
Yes, please.
We gave more time for Professor Takahashi.
Sorry.
We have more 40 minutes and 5 minutes for questions.
Sorry, that's true. Equatorial plasma bubble observations, past and present, and we have 40 minutes, right? Okay.
Yeah.
Please, Dr. Takahashi, go ahead. And thank you by your presence. Your microphone is not opened. Please activate your. Okay.
Yeah, you hear
now? Now, okay. We got it.
Okay.
Thank you.
I will compartilhar a tela, né?
All right.
This one is. This one is here. And this is here. Okay, now it's okay?
Yes, it's all right.
Okay. Good day for everybody. I'm talking from São José dos Campos, São Paulo, Brazil. My talk is about equatorial plasma bubble observations in the past and present. It means kind of the a historical survey of our observation about the plasma bubble and what we are doing now and what we want to do now for the future. Just kind of a talk with you about what we're doing. So there are no specific scientific subject, but I will show you some kind of general aspect of this plasma bubble observation and investigations. Because of this, a lot of work has been done by the many people here. My co-author is like this: Takahashi, Rassi, Figueiredo, Baus, Paulino, Medeiros, Buriti, Essen, Abdul, Otsuka Shokawa, and Ines Batista, and Sobral. So I am talking what we have been done up to now. So I will first talk about what is equatorial plasma bubble very shortly and how we have been observing it since 1970s. Today, the theme of science and looking for a new horizon. Mainly for the students, I'm looking for many students hearing this talk. So my talk is more some basic things. Ionosphere, which I'm talking, is from 50 to 1,000 kilometers above this Earth's surface, where we have a lot of ionized materials, mainly atomic oxygen and ionized oxygen, and so it's a state of the ions and state of the plasma, because number of ions and number of electrons are almost the same. But they're not stable. There's some kind of dynamics there, waves propagating or plasma bubble, which I'm talking now. So this is a very dynamic area. So several interesting points we have in this area. What is the equatorial plasma bubble? First, I want to show. It's a very popular picture here, showing the, what you say, let me see, pointer here. Okay, Earth looking from day side here and night side here, and the evening side here. We have some kind of this is the magnetic equator here. We have some kind of irregularity or kind of depression in the plasma, and instead to go to the down, but it's going to develop in this state here, and larger and larger and higher and extending to the magnetic south and north side, extending this magnetic meridian here to go to the midnight. This is a kind of a story, a scenario of the development of the plasma bubbles, starting from around 250 kilometers of altitude up to the 1,000 kilometers, very high. So it's very dynamic. What science we are doing, and what is the social and technological concerns about this one? The science is why does it happen? Everybody wants to know about this one. And mechanism of ionospheric disturbance. Why it's going to develop instead of to go to down. Huh? And can we predict this kind of irregularities or bubble development or not? This is our science is doing. Social and technological aspect is the ionospheric irregularities cause radio wave propagation irregularities. It means, example, telecommunication systems, and also today is more important, the GNSS positioning systems. You don't want to have error in your positioning. Your car navigator has an error of the few meters, it's okay today, but in near future, you cannot have error of the few meters, should be few centimeters. So this sort of thing is very important issue for the society, technological society here. So how we have been observing it since 1970. Many people didn't born in the 1970, but this one started in the 1970. But I'm talking about mainly about air glow observations. Their long history of the ionospheric observation by the ionosonde, the radars since 1940 to 1950. But talking in my case only about air glow observation here. We started air glow observation in Brazil in 1971, 72. First air glow photometer is this one. We design and construct here at INPE in San Jose's campus. The first tilting filter photometer measuring the oxygen air glow green line, which call it 5577, and the red line of the atomic oxygen 6300 emissions. This is very popular emissions in the aurora and air glow here. Detector is a photon multiplier. So looking at one point of the sky to measure the intensity from the ground, to measure the total intensity of the emission layer, which go in the 100 kilometers of altitude. So taking this data in kind of analog for the photon multiplier and amplifying this is the say 1,000 times, measuring some voltage in terms of the millivolts or microvolts per millivolts, detecting and registering in the chart papers. I think many people don't know about the chart paper, but our science started with this one. All night taking some data on the chart papers because there's no CCD camera. I think first detection of some kind of plasma depressions measured by the 6300 is this publication in 1970, I think 1974. Measure is at Agulhas Negras mountainside in the state of São Paulo. This air glow photometer measured this sort of depression of the 6300 from 700 radius to the 300 radius here. But we didn't know about this one. Why it happened? So maybe at that time, Dr. Sahai, who wrote this paper, he put this one due to the geomagnetic activities in this night. So kind of large intensity fluctuation because of the geomagnetic activities. No knowledge about the plasma bubble structure here. But in 1978, Dr. Sobral and Dr. Sahai published one paper to the another, showing kind of the depression. Now, this is some depression here, together with another data about the rheometers and this ionosphere data, and discussing this one due to the plasma bubbles. Because in this time, 1975 and 78, there are several observations from the United States using satellite also, OGO 6 something satellite data. People already know about the, some kind of depression is happening near the equator. So this sort of, they be called the plasma bubble. We appointed this one due to the plasma bubble. So more clearly, you can show in the Sahai's paper, 1981. Look here. This is nighttime observation of the 6300. Also, another emission of the 7774. This is also oxygen near infrared emissions here. Very sharp decrease of this intensity here. Also, Sahai said this is due to the plasma bubbles here. But in this moment, we have no idea about the 2D dimension only 1D, only vertical things, 1 point, but photometer. Okay, so we have to wait up to the, but these almost 20 years of data by the aerophotometers, Sobra published some kind of seasonal variation of the occurrence of the plasma bubbles, much higher occurrence in the January, February, and November, December, but less in June, July. So kind of climatology of this one, we already started to observe in the I think this is paper 2002, huh? Okay, but okay, another one is the rocket observation, 1985 from Natal, Sonda 3 rocket observed the vertical profile of the irregularity of the electron density here. This sort of observation by the rocket, this is in situ, vertical profile. The first time we detected this one. But up to 2000, I think there are 5-10 rocket experiments carried by the Dr. Abdul and Polinaya people. There are, I think, more than 10 profiles of this vertical profile of the irregularities also we started to see. So this is the vertical things. Huh? We have to wait up to 1997 about the image observation using charge coupled device detectors. It's the first time a two-dimensional picture of these bubbles observed by the green line here and red line here, and almost same, but resolution is not so good, and time integration is longer, so it was not so good if you compare with today's one. But this is the first observation of the two-dimensional air glow observation by the all-sky image camera. First result which started to see in the paper is the, I think this is a August magnetic storm condition in 1998. Abdul published this one, which also this is it's not corrected about the all sky image here, but you can see whole night plasma bubble structure here up to the early morning. You can see. So this is the first historical results of our image observation data. I think this time also at that time our student, PhD student, Amaury Fragos Medeiros, also participated in this observation and this investigation here. And air glow image at San Juan de Cariri in Paraíba in 2000 started the observation of the imaging observation of the equatorial region here. Here is Professor Amaury here. This is not, this is a 2003, so it's 3 years after. This is a 2011. We took a good picture of this sunset, and you have an image here. Okay. So this is also very popular and famous all-sky image of the oxygen red line. Professor Amaury put some color in the red to see very nicely. And you can see some bubble structure here. And anomaly is the southern sky of the Cariri, you can see very nicely. In 2002, we have a equatorial ionosphere campaign. At our case, we put this image in the Boa Vista, the northern hemisphere, And you can see some kind of periodic structure with the bubble here. From the north, this side is equator, huh? And you can see anomalies here. Something you can see. Okay, this is part of the observation of the plasma bubble by the images. But I have to show about the equatorial plasma bubble observation by the satellite. Quite recently, more than, but not recently, only 20 years from here. Before 2000, we have several photometer observation by the satellite from the United States, but just talking about after 2000. Time satellite has a very nice data set provided us, has several, 3 or 4 instruments on board. And we have a GUBI, global ultraviolet imager, and also with SABRE observing the air glow here, which is very nice data. One of the very nice pictures is the GUBI data making with several nights observation put together to see anomaly structure over the equator here, northern hemisphere and southern hemisphere. And you can see kind of a depression here. This is a plasma bubble here. So I think this is one of the first pictures showing the global structure of this plasma bubble here. And this is over the South America, okay? It's very nice. After 2008, CNOS, this is the American Air Force, launched equatorial orbit satellite, which have several ionospheric sensors here, measuring the ionosphere in the equatorial regions here. One of the equipment measuring the ion density in situ. It means this satellite is low orbit, low Earth orbit, around I think something like 300 kilometer and the 300, 400 kilometer in the lower. So measuring the in situ along the, this is longitude, around there, this is Europe to Africa here. This is the African side here. You can see depression, very nice depressions, many depressions, especially resolution very high. And this is due to the plasma bubble here. Now, one orbit to the another. So this sort of some detail of this plasma bubble structure we can observe and investigate from the satellite. And more recently, 2018, just 2 years back, launched 2 satellites. One is for the very high altitude. It means almost geostationary. It means almost stop to the geographic coordinate here. And mainly this kind of geostationary satellite is over Brazil because this is should be over the equator. Huh? So this one measuring the one thing, and another one icon measuring the another one, which also this is also near equatorial orbit. The lower altitude, I think some around 630 miles, it means maybe 600 kilometers, something. So these 2 satellites measuring the same phenomenon and this observing the ionosphere here. Some data, you can access this web page to find out what is the perhaps ionospheric connection explorer icon, and this gold is a global scale observation of the rim and disk. So these 2 satellites already producing very nice data. So many people starting to get this data to work on it. I think this data is available for who has interest to study. So we can access to this data to start to work like this. Another technique, equatorial plasma bubble observation by the TEC-MAP, using the ground-based GPS or GNSS receivers. The principle is very simple. GNSS satellites normally have two frequencies of the radio frequency transmission toward the Earth. This two frequency different optical path because of the different frequency. So difference of the phase between the two frequency is a proportion to the number of electrons along the path here. It means this, what you call the slant. Slant TEC is proportional to the phase difference. So taking these things, we calculate the total electron density here. The great advantage, this sort of things, you can do by the one ground-based
Ouve, tá, acho que perdeu o sinal, né?
You're not looking? Is it
Hello.
okay?
I think he lost the signal, maybe. Let's wait for a while.
Shall we do
okay.
It's okay?
Okay, now we got it.
Okay.
Are you listening? Are you listening?
I'm hearing well.
Okay.
Are you yes, I'm listening, yeah, hearing well.
All right, thank you, go ahead.
Okay, so almost 140 ground-based receivers making the observation of the TEC, total electron content. And each one has 4 or 5 GPS satellite or GNSS satellite. So we have almost 600 to 800 plot of the observation of the TEC. This is a great advantage of this sort of observations. You can cover whole South America here. So this is another result of the TEC-MAP made by the Space Weather Center here in INPI. But this is 2014, it's almost 6 years back. Today, a number of the observation increased because of the number of the receivers increased. So we have a better resolution of the specialization of the TEC-MAP here. But you can see this kind of the depression, blue is kind of the 0 to 10 TEC, and green is something 30, 40, and this red is 60, 70 TEC units. So this is the low level, and this is high level here. So this is anomaly area here, and this is a magnetic equator here, and you have 1, 2, 3, 4, 5 depression area. So this is we call it plasma bubbles. So we can make some snapshot of the TEC-MAP showing the plasma bubble here. Each 10 minutes we have this picture here. So time evolution one night from the 23 UT means 8 p.m., 8, 9, 10, and 11. And you can see development of the bubble here. Looking to one night to the another, February 10, 11, 12, looking at the same local time, okay? 13, 14, 15, 16, 17. You can see every night, each night have different structures. The stronger and this kind, you have no good development here, but only here in the western coast of the South America. So each night a different feature of the plasma bubble here. So this is one of the reasons which we want to study why some day-to-day variability of this sort of plasma bubble here. So today's themes of science, what we're doing now is who is seeding, what is the seeding process? Who causes this sort of irregularity and developing? So one of the things which are looking for is before the, this is the 2136 UT, it means 6:30 in the afternoon. Some perturbation with the TEC. This perturbation is very small. This is 0.1, 0.2 TEC unit. You have 50 to 60 TEC unit, but only looking at some perturbation, disturbance, small disturbance with the less than 1 TEC unit. And you can see this sort of low and high, but the only difference maybe minus 0.3 to plus 0.2. This sort of things, we call it just a medium scale ionospheric disturbance, MSTID. It's a kind of wave structure, wave propagation, wave structure in the ionosphere, happen in the sunset or prior to the sunset here. And after you can see half an hour later, you can see development of the EPB, plasma bubble here. So we believe that one of this kind of perturbation before the sunset caused this plasma bubble outside. This is one thing which we are studying now. Another one which we started to observe is the plasma bubble irregularities, plasma bubble dynamics. This is a picture which we got in last year, December, this one, showing this plasma bubble. Eastern side is very straightforward, but west side some kind of interaction atmosphere, making some kind of the, we can call it kind of the structure of the Kelvin-Helmholtz instability like this. So maybe this is plasma bubble and atmosphere, some interaction here, or maybe some kind of wind behind. So this is now it's studying by the one of our colleagues here. The another one is the plasma bubble here, and this is a dark band is a kind of MSTID wave structures at nighttime propagating from the east to west, and it interacts with this plasma bubbles. This is a very nice picture showing the two things. One is the plasma bubble and waves propagating from the, normally this plasma bubble going to the east and this one go to the west. So what happens when you strike one to the other like this? So this is just in last September, we observed from the Bon Jesus Lapa. This is a new observatory. This is a new observatory, which I can show you, which stay localized up to the 13.2 south and 43 point west. Here, we set up this observation site in the 2019. This is a container which we set up here, and this is the air glow imager here. So this is a very nice data which giving us a little bit different of this, which we observe from the San Juan de Cariri here, the 7 degrees south here, and also from the Cachoeira Paulista here. So we are expecting more same kind of plasma bubble. Putting this one, we can get some good, different kind of plasma bubble structures we can observe here. So this is a very, very nice. So looking for new horizon, which I want to talk with you about new horizon now, what we want to do, we are looking for some kind of campaign with the equatorial plasma bubble observation campaign, which we discussed in last year, September, how to organize this sort of things. And we wanted to start in 2020, but due to this pandemic, we are postpone this sort of campaign observation here. But originally, our idea is to put some observation side here from the eastern coast to western coast, including this Hikamarka observatory here with collaboration, and also from the northern hemisphere, Boa Vista to the Santa Maria. So this area, we want to put some ionospheric Fabry-Perot interferometer, imager, VHF radar, VLF radars, Lambda something. So this organized ground-based observations, we want to know about the plasma bubble generation seeding process and how longitudinal variabilities of this seeding process here. Yesterday I got this picture from Dr. Cristiano about the future imager network here. This is the, from the far west part of the Brazil here to the São João do Cariri from the eastern side here. So covering from -35 to -65 degree, and also from the up to the Santa Maria here. So this is our near future observation. Oh, talking about the future new horizon, but in Campina Grande, you already have a pioneer about this sort of observation here. I want to show this this guy who looked for a new horizon in Japan and in Antarctica. So he's one of the first pioneers of the Campina Grande about our area, Professor Ricardo Borici. He went to Japan, taking his photometer to measure the OH temperature together with the MU radar in Kyoto University. After he went to Antarctic, taking this but different OH temperature photometer to measure the temperature of the King George Island. It's very nice data. Up to now, we have no other data except his data at that time. This is 2002, this one now. Another professor, pioneer of Campina Grande, Professor Mauri Medeiros, who started the imaging observation of Agro is Professor Mauri Medeiros. His first work in the Campina Grande, São João do Cariri, and here's a nice picture here. So he started Agro imaging and image at São João do Cariri. Another much more recent pioneer of this about the atmospheric gravity wave. She studied very hardly about this issue, and he made some kind of what you say ray tracing technique. Also, he developed. And today, many people here in Brazil using this one. And also his activity in the conference is like this, is in the Praha 2011. Here is he, and who know, you know about this one, and you know about, many people know about Anna, and the other people here in the Praha in that time. Wow. This is another pioneer of Campina Grande, Professor Lorivaldo of the State University of the Paraíba, who studied the atmospheric planetary waves here. So each pioneer taking each area, which key area of our atmospheric sciences. So we were very nice to have good people in Campina Grande to get working together. So my summary is that equatorial plasma bubble, one of the main issue or main theme of atmospheric science in Brazil. Brazil has contributed in this subject with international space physics communities. So new technological aspect opens a new horizon to progress our knowledge. So I just show you about we started from the photomultiplier, from photometers, go to the imaging devices to expand for two-dimensional investigation of the air globe. Today we are using satellite data, also GPS or GNS data also. So I hope that all the students in the Campina Grande, they have a chance to open a new horizon for our future work. This is all I want to show you today. Thank you very much.
All right. Thank you,
okay?
Dr. Takahashi. Thank you very much for your nice talk. Do you have something more to show, or?
No, that's all.
All right.
That's all. Yeah.
So we know of the historical tradition that you have in the National Institute for Space Research. We have several people here have studied with you guys from the institute. So this one of the last slides that you show, you are planning to install new equipments through the spread around the country and Peru. Is that correct?
Yeah, in this campaign, we are planning to set up new agro imaging site, I think Porto Velho, in Rondônia, and also in the
Rondônia.
Yeah, Rondônia.
I see.
And the Amazon region too.
All right.
So Dr. Cristiano is contacting with the people to set up this one. Yeah.
Which equipment you are planning to install in Rondônia,
yeah,
please?
Air glow imager.
Air glower.
Okay. Air glow imager, yeah.
Air glow imager. Okay. And there is a chronogram for that, estimative for do that?
At this moment, we are waiting some kind of discussion about this campaign to when we want to start this organized coordinated observations scheme. Not this year, of course, but maybe next year, 2021 or 2022. So we have to discuss with our colleagues about this point. So at this moment, we are in the pandemic.
I see. All right. Anyone else want to make a question? We have 1 minute.
Fernando, I have a comment.
All right, go ahead.
Professor Takahashi, thank you so much for this interesting review. It was really nice. I enjoyed it. Congratulations for this, your beautiful history about the research in aeronomy in Brazil. And we appreciate, of course, your contribution for the development of our research here in Campina Grande. thank you so much, and we appreciate your time.
Oh, thank you too. Yeah. Oh, I hope that we continue this sort of coordinated observation with your group here. Yeah.
Yes, Dr. Takahashi has been developing, along with the staff of the National Institute, very great work, and I don't know. It's it's an honor to me. Sorry. Actually, it's an honor to me to be invited as a chairman. I want to thank you for. I want to thank for the local organizing committee and Igor, João, and Buriti, Amauri. Oh, everybody. Thank you for inviting for this to be chairman. And I want to know if you have some other comments, or we can close the session.
Okay, Fernando, thank you so much for your participation here. I would like to thank for all the speakers this morning. It was a pleasure to hear from you your research and your perspective for the future. We thank for all the participants to attend this morning, and we invite everybody to come back at 2 p.m. in 1.5 hours. Okay, and see you there. Thank you so much.
All right, so to the next session. Have a good afternoon for all. All right, all the best.
João, are you there?
Yes. I'm going to inform that I am up to send the invitations for the speakers in the afternoon section, and I'm just going to turn off the live transmission there in YouTube, and also I need to close this section here in order to open the next one and invite the next panelist. So everybody can access the next section with the same web link as a participant, or you can also use the Eventry platform to access this room again. Okay.